Okay, good morning, everyone, and thanks for coming for all the week. And we are in day number 6. So today, our first speaker is Professor Nikolai Rechdikin from Tsinghua MSc, Tsinghua University, and he is going to speak on stratified superintegrable system. So let's welcome Professor Rechdikin.
Thank you. So it's the same title, but different letters. It's on geometry of superintegrable systems. But one of the interesting piece of this geometry is that in many real cases, such systems live on stratified symplectic spaces, and all the ingredients, Poisson manifolds and everything else, they have a certain stratification. So it's a real pleasure to give a talk at in this audience. I always was thinking that I'm not working in geometric analysis, but then after some short re-evaluation, I realized that I do. Because what are integrable systems and superintegrable systems? It's a geometrical tool that replaces analysis by geometry. And I will explain how it does it. So, okay, let me first remind what a Hamiltonian integrable system is. So suppose that we have a symplectic manifold, dimension 2n. So symplectic manifold means that the manifold is equipped with a non-degenerate closed two-form omega. The two-form can be considered as a mapping from the tangent bundle to the cotangent bundle. Non-degenerate two-form means that it's an isomorphism, it's invertible, and the inverse of omega is a bivector field. So you can pair this bivector field with the form df dg, and this is called Poisson bracket. So and an integrable system on such manifold, it's a geometric structure. So I want to distinguish between two very closely related things: integrable system as a geometric structure and an integrable system as a dynamical system. So now we're looking at the geometric structure. So the usual way how you can find it in the books, it's you have n functions on 2n dimensional symplectic manifold, which are in the involution, meaning that Poisson brackets are 0. And these n functions, they give a mapping from m to n to some region in Rn, the region where these functions take values. So it's a projection. And the generic fiber is a Lagrangian submanifold. So it's a Lagrangian projection. Generic means that these functions are independent on this fiber. So in a nutshell, an integrable system is a Lagrangian fibration where the Lagrangian means that generic fibers are Lagrangian. And then there is Liouville theorem, which says that flow lines of Hamiltonian vector fields of these functions, they define an affine coordinate system known as angle coordinates on these generic level surfaces. So generic level surface is always isomorphic to Rn times a torus. If it's compact, then it's a torus. And in the neighborhood of the of such generic level surface, omega can be written in this way. So in other words, Fi and theta I are Darboux coordinates. So, but there are several issues with this. First, there are singular level surfaces, and Bn is typically not a manifold, but a manifold with boundary, with corners, and so on. So in the compact case, so in any case, when we have the flow lines, commuting vector fields, the flow lines of these vector fields, they define an Rn action on our manifold, which we can call phase space. So if the manifold is compact, then there is a toric action, and then there is a beautiful description of the image of P, which can be regarded as a moment map for toric action. It's a convex polytope. There is a theorem about it, about the convexity, but then there is a very precise description of this polytope by Delsant, this type of polytopes. So this can be made more general. So one can say that an integrable system on a symplectic manifold is just a Lagrangian fibration, which means that generic fiber is Lagrangian, but there are also singular fibers. So these functions f1, fn that appeared earlier, they can be regarded as local coordinate functions, and the Liouville theorem holds globally. So algebraically, this means that in the algebra of functions on M, and what type of functions we consider, it depends on the setting. Say if these are real smooth manifolds, then these are real smooth functions. If these are real analytic manifolds, then these are real analytic functions, and so on. So algebraically, it means that in our Poisson algebra of functions on the symplectic manifold, we have the maximal commutative subalgebra, and Poisson algebra. It's a beautiful subject that I think, it's a beautiful subject. Why Poisson algebras is are beautiful objects? Because these are the things that have two structures. It's a commutative algebra with the pointwise multiplication of functions. It's a Lie algebra with the Poisson bracket. And the Lie algebra acts by derivations on the commutative algebra structure. So it's a kind of two-component structure. And you can think of Poisson algebras as first jet of deformations from the kind of category of commutative algebras to the category of associative algebras, general associative algebras within the category of associative algebras. Okay, and so geometrically, an integrable system is a fibration where the generic fiber is Lagrangian. Algebraically, it's this maximal commutative Poisson subalgebra. I think so. I mean, it's one of those cases when the name is given fairly. I mean, I have to check, but I think so. Okay, so now integrable dynamics. So if we have a function that's a pullback from the functions on the base of this vibration, then the main thing about integrable systems is that in the angle coordinates on level surfaces, the dynamics is linear. And these are the frequencies or rapidity or velocities in which the system goes along these coordinates. So if we have a dynamical system whose Hamiltonian happened to be of this structure, then we solve differential equations. And that's a kind of super geometrical analysis. We solve differential equations without analysis. So, of course, there is a cheating somewhere here, and the cheating is that it's very rare that dynamics is integrable, and to construct these angle variables is kind of non-trivial task. But it is true that if you have angle variables, then you solve differential equations. So now there are many interesting examples, and first examples appeared. I think first example of an integrable system appeared in the work of Euler. The rotations of the solid body. And then there were the number of finite dimensional examples grew and grew steadily. But then there was a gap in the early 20th century. And then there was a remarkable discovery of integrability of nonlinear PDEs, like Korteweg-de Vries equation, KP, Kadamtsov-Petriashvili equation, these equations that appear in the hydrodynamics. And then after this, with the new techniques of Poisson-Lie groups, now there are infinitely many finite dimensional and infinite dimensional examples like this. So this is all Liouville integrability. It was a very brief overview of basic structure. So now, what is a superintegrable system? It's a terrible name because there is nothing really super there, but it's the name that stuck. So the original name was degenerate integrable systems, which is more appropriate. But okay, we'll just accept this. So again, there are super integrable dynamical systems, and there are super integrable systems as a geometric structure. So again, let's fix our symplectic manifold. It's a phase space of our potential dynamical system. So it doesn't have to be smooth. I mean, it can be stratified by smooth pieces. And we will see examples of this. A superintegrable geometric structure is the following. It consists of two projections. From our symplectic manifold to Poisson manifold of dimension 2n minus k, and from the Poisson manifold to the base of dimension k. Now, all maps are Poisson. They preserve the Poisson brackets on corresponding algebras of functions. So this is a Poisson manifold. This is a Poisson manifold with the zero Poisson structure, meaning that the Poisson brackets are trivial. So the requirement is that the fibers over here are coisotropic. There are several equivalent ways to say it. In particular, we can observe that once it's coisotropic, then these fibers, the fibers of P, their connected components are symplectic leaves of this Poisson manifold. Typically, Poisson manifolds are, so a Poisson manifold meaning that it's a manifold with the bivector field such that the corresponding Poisson brackets satisfy the Jacobi identity. So, so they have symplectic leaves. These are submanifolds where the restriction of this Poisson bivector field is non-degenerate. And so this is the structure. So we have two projections. Fibers of the lower projection are symplectic leaves of P, and fibers of psi, they are k-dimensional isotropic submanifolds in M. And I emphasize the word generic, meaning that there are also singular fibers. Okay, so that's the replacement to Lagrangian fibration. If we forget about this intermediate piece, if k equals to n, forgetting means that if k equals n, p is equal to b. In this case, we come back to the Liouville integrability. So everything that we can ask about Liouville integrability, we can ask about such systems. So now let me say a few more words about them. So for coisotropic submanifolds, there is something that's called symplectic reduction. What does it mean? So if we have a symplectic manifold and some coisotropic manifold X, so here we have the two form that is closed, but it's degenerate in the sense that the mapping from the tangent bundle to the cotangent bundle has a kernel. So kernel is so it's an integrable distribution, and the space of leaves of this distribution is the symplectic reduction. So we have this structure. Yeah, the fibers here are symplectic reductions of the fibers of the total map, of the composition map. So then there is an old theorem by Nikhoroshev, which is basically the super generalization of the Liouville theorem. It says that the fibers of psi they have natural affine structure, again, angle variables, and then for generic point P, the fiber is isomorphic to RL tensor, to Cartesian product with a torus, and sorry for the typos. These fibers can degenerate as P varies over this intermediate Poisson manifold, something that you don't have the room for in the usual Liouville theorem. And then finally, in the neighborhood of a regular fiber, the symplectic form is not just the usual Darboux form with action angle variables, but there is an extra piece that's coming from symplectic leaves of the intermediate Poisson manifold. So there are plenty of examples of such systems, and actually, first example appeared even before Euler. It's the Kepler system. So I think it was the uncle of Euler who actually studied Kepler system systematically and who first discovered so-called lens vectors. So for Kepler system, there are components of the angular momentum tensor that are preserved, but there are also these very special vectors, so-called lens vectors, that are preserved. And actually, this was discovered by the Swiss mathematician. I forgot his name, but he was one of the uncles of Euler. So then Mishchenko, Fomenko had several examples related to the algebras. And then after this, there are infinitely many examples. And today, at the end, I will explain how to produce examples of superintegrable systems from modular spaces of flat connections over surfaces. But before continuing, let me, I can use this. So let me say what it means algebraically. So algebraically, it means that we have our Poisson algebra of functions on the symplectic manifold. In this algebra of functions, we have a subalgebra, J. These are functions on P. I didn't write it here, but that's functions of P. And then in this algebra, we have the subalgebra of the Krull dimension K, or just functions on the on B. It's just a dual picture to these projections. In terms of functions, you will have embeddings, and these are the embeddings that I'm talking about now. And then algebraically, what it means is that we have the Poisson algebra A, and then in this algebra, Poisson algebra, we have a commutative Poisson subalgebra. Now it's not a maximal commutative Poisson subalgebra, but Poisson commutative subalgebra of rank K, and then it's embedded in its centralizer in the algebra A. And typically, if you just take, say, K equals 1, you have a function on your phase space. How many functions will Poisson commute with this given function? Typically, none, except for some combinations of this function. So, but in some exceptional cases, you will have a big centralizer. And 2n minus k is the maximal rank of the centralizer of such Poisson commutative subalgebra. And so superintegrability means exactly this, that we have a Poisson commutative subalgebra, rank k less than n. If k is equal to n, we are back in the Liouville situation. But its centralizer has rank 2n minus k, which means that in this centralizer, there are plenty of independent functions that are preserved by the dynamics of these functions, which means that we have Poisson commuting Hamiltonians that generate this k-time flow or k-independent commuting Hamiltonian vector fields. But then these vector fields, they preserve a lot of functions, not just the functions that generate these vector fields. So kind of intuitively, you can think of this as an integrable system that locally looks like this. It splits into two k-dimensional usual Liouville integrable system and 2n minus 2k kind of trivial cyclic variables that are not moving, that just constants. So, but it's a local splitting. Globally, you cannot do it, and so that's a non-trivial feature of these systems. So now, yeah, I already started to talk about superintegrable Hamiltonian dynamics. So if we have a function h that's function on the base, then just as in the usual Liouville theorem, the flow lines of any such of the Hamiltonian vector field generated by any such function are linear in angle variables. The functions from on P are preserved. So these are the first integrals. So this situation is also known as non-commutative integrable system when you have k Poisson commuting Hamiltonians and then lots of Poisson non-commuting first integrals. So so kind of if you want to be poetic, you can say that these functions on fibers of projection P, they describe some internal symmetry of the system. So that's the symmetry in these cyclic coordinates. So there are natural questions, there are many natural questions. One of them is what happens on singular fibers? And for Liouville integrability, it's being studied quite a lot within the works of Fomenko and this school of thoughts. But here the situation is much more flexible. And as we will see in this example of spin Calogero-Moser system, it's quite interesting. So let's say that G is a simple compact Lie group. We trivialize the cotangent bundle by right translations on the group. So now it's just a trivial bundle, the dual space to the Lie algebra across the Lie group. And so the cotangent bundle to G is, as any cotangent bundle, is a symplectic manifold with the canonical symplectic structure. So our Lie group acts on the cotangent bundle. After trivialization, it's just a diagonal action, the coadjoint action on G star and the conjugation action on the group. This action is Hamiltonian with the moment map that's given here. It goes from the trivialized cotangent bundle to G star. And I wrote this for matrix algebras. This is the coadjoint action of G on X, which is, if G is a matrix group, then it's just a conjugation. So, so then what it means is, in particular, it means that if you take the quotient space T star G mod G, it's a Poisson space. Say, if it would be a manifold, it would be Poisson manifold. But in reality, such space is practically never a manifold. It's singular. It's actually a so-called stratified space. So if we will ignore these features, so then it's the same theorem as for in the smooth case. Symplectic leaves are given by the Hamiltonian reduction. So what you should take is you take the pre-image of a coadjoint orbit and then mod out by G. So so that's a kind of complete geometric description in some sense of this space. So it's a Poisson space, and these are symplectic leaves of this Poisson space, which are themselves symplectic stratified spaces. Okay, so in this case, the stratification is so-called Lerman-Schmar stratification. It's given by the structure of the stabilizer. So, so this stratum is where the stabilizer is isomorphic to the subgroup H in G. So this H in the bracket means the conjugacy class of the subgroup in G. So it's the equivalence class where H prime is equivalent to H if H prime is conjugate to H in G. This is a stratification in the sense that there is a partial order on these conjugacy classes, partial order by the inclusion. The class H prime is not greater than the class H if H prime is a subgroup in H. And then the closure of the stratum parameterized by H is the union of the stratum that are not greater than H. So now, how to construct? So why did I start to talk about these cotangent bundles? Because there is a natural family of superintegrable systems on that can be constructed from these cotangent bundles. So let's consider the mapping from T star G to G star cross G star. It's a fibered product over the space of coadjoint orbits in G. So the mapping, it goes like this. After the trivialization of this bundle, the pair XG goes into X and then minus coadjoint action of G on X. So the left side X, the mapping from this pair to X, is the moment map for the left translations by G on T star G. It's again a Hamiltonian action, and that's a left moment map, and that's the right moment map. So this mappings commute with the G action. They are Poisson mappings. This projection from such pair to down to X is also Poisson map, obviously. So we have two Poisson mappings from T star G to this space and then down to G star. They all commute, everything commutes with the G action. So G action here is just a diagonal coadjoint action. And then as a consequence, we have the this mapping of these two mappings of Poisson spaces. And the theorem is that if we restrict these mappings to any symplectic leaf of this Poisson space, then it's going to be a superintegrable system. So symplectic leaves in this case, they have very explicit description. So these are the pairs of elements from G star cross G, such that the moment map belongs to O mod G. So this is just the original definition. It's mu inverse of O mod G. The psi mapping is given by these projections. So as I said, left projection is the left moment map, right projection is the right moment map. So this Poisson manifold can be characterized as elements from this fiber product such that x minus y belong to the orbit. And then the projection down below is just projection to x. And this space, the base, it's a subspace in G star in the space of coadjoint orbits. And it's the space of x's in G star such that there exists G such that x minus coadjoint action of G on x is in orbit O. So very explicit description, three spaces. S is symplectic, P is Poisson, B is just some space. And the theorem is that it's a superintegrable system. So in particular, any function on B pulled back to the symplectic leaf gives the superintegrable dynamics. So all these spaces are stratified, and then I'm advertising almost completed work with Cheng Zhou, Kai Jiang, and Fuseling Xiao. So that's one of the small pieces of this work, an example for SU3. So let's look at SU3 example under the microscope. So let's fix, so it's, in this case, the algebra is just the algebra of Hermitian 3x3 matrices traceless. So let's say Xi is the diagonal matrix with entries Xi1, Xi2, Xi3 such that trace is 0. By the action of the while group, we can order them in this way. So C3 must be negative in order to this to be satisfied. So then geometrically, these vectors are elements of the Cartan subalgebra for the compact real Lie group SU3, and there is a stratification of the principal Weil chamber. It's so the principal Weil chamber is something that's in between of two fundamental roots. So the inside is the interior. That's when all X's are distinct. And then there are two walls, where one is where Xi1 is equal to Xi2, the other is Xi2 equals to Xi3. There is the origin, that's the most singular point. But then there is a very special line because the Weil chamber has a symmetry, the reflection with respect to this wall. So there is an extra special ray. Okay, so then I will denote as Xi the symplectic leaf corresponding to the coadjoint orbits through Xi. And then if Xi is in the interior of the principal Weil chamber, then and Xi is not on this very special ray, then it's a smooth manifold. There is no stratification. If Xi is on any of the two walls of the principal Weil chamber, it's a smooth manifold. It's the cotangent bundle to the regular part of the Cartan, mod out by the Weil group. But if Xi is on this very special ray, then there are two pieces in our stratified space. They are classified by the stabilizer as before. It's this orbit type or Lerman-Schmarr stratification. That's a detailed description of the strata, which probably I shouldn't discuss for too long because there is not enough time. But the important fact is that there are different symplectic leaves. There are smooth manifolds, and then there are stratified symplectic leaves. Okay, so then there is a notion of stratified superintegrability. Again, I don't want to go into the details of this formula. Instead, let's look at the picture. So what happened in this case? So this is the picture. This cone is the principal Weil chamber. So the green region is the base of the fibration. So that's B. You can see that B is bounded by these straight lines. So it's, if you forget about the interior structure, it's a kind of cone type semi-infinite polytope. And remember that we have two projections. Yes. So if our point on the base is inside, really inside of this green region, then the fiber P is two-dimensional. It's a two-dimensional symplectic leaf, and over this two-dimensional, so we have a point B in here. The fiber P inverse B is a symplectic leaf in P, and then over this fiber we have a Lagrangian, not a Lagrangian, we have an isotropic fibration, the projection Psi. So over these fibers P inverse B, we have a two-dimensional Liouville tori. And as we move along this fiber, they're still two-dimensional, they don't degenerate. So over the boundary, we have one-dimensional Liouville torus and zero-dimensional symplectic leaf. So here there are corners. If we take any Hamiltonian that's a function on the base, this will be fixed points of the multi-time Hamiltonian flow. In this case, it's two-time evolution because we have two independent functions on a two-dimensional base. So, okay. So here the fibers are one-dimensional everywhere. Here the fibers are two-layered. We have a two-dimensional symplectic leaf and two-dimensional fibers, the Liouville tori. Over each of these two lines, we have a two-dimensional symplectic leaf, but the Liouville tori, as we move over this two-dimensional symplectic leaf, they can degenerate into one-dimensional. So they're quite singular, not quite singular, almost regular, but a little bit singular. So the intersection point is interesting. It's not a fixed point. It's just where, so the fiber here is still two-dimensional, the symplectic leaf. But as you move over this symplectic leaf, there are two places where two-dimensional tori can degenerate into one-dimensional tori. So you can see that it's quite nice, non-trivial picture of the generations. And for example, these features that the Liouville tori degenerate into one-dimensional over something, it doesn't exist in the Liouville case. So there is something, there are several things to investigate here. So then there are several conjectures. One, which kind of almost a theorem now, is that the symplectic volume of these symplectic leaves is piecewise linear, and it's constant inside the inner cone. The inner cone is this cone, that's inside. And this is very much related to the Horn's conjecture, to the Horn's theorem about the eigenvalues of three Hermitian matrices, and about the structure of the Littlewood-Richardson rule for the tensor product of two irreducibles in SUM. But I have no time to talk about this. Yes, I have only 3 minutes. So then singularities of integrable systems, that's nice kind of subject to sort out. And then finally, something that I'm not an expert on, but I'm kind of very curious about this, because there is this paper by Strominger, Yao, and Zaslov about the structure of mirror symmetry. So if you have a Calabi-Yau manifold that's fibered over the base by some kind of tori, then the mirror symmetry is just you map the fiber to the fiber with the opposite period matrix. So here there is certainly more flexibility. So you have fibers that are not Lagrangian fibers, not Liouville tori, but isotropic tori. So it's one of the questions. And then I have 2 minutes to explain that you have infinitely many superintegrable systems on modular spaces of flat connections over surfaces. So let's fix a compact simple Lie group, compact oriented surface with possibly several boundary components, some simple non-intersecting, non-self-intersecting closed oriented curves on sigma, such that their homotopy classes are pairwise different and distinct from the boundary components. And let's fix n conjugate classes in G. So then we have this modular space of flat connections on sigma with given holonomies around boundary components, not given holonomies, but given conjugacy classes of holonomies. And it's also known as character variety, relative character variety. It's well known that it's symplectic for closed manifolds, as Atiyah-Bott theorem. And then let's define, for this symplectic manifold, let's define the Poisson manifold in the following manner. We will cut sigma along these curves, and we will say that impose one condition on the holonomies. So the holonomy, so we cut and we separated sigma like this. So now the holonomy on this part of the surface should be conjugate to the holonomy on this part of the surface, because then we will be able to glue it back. So this is the Poisson manifold, and the base manifold is the space of all conjugacy classes that we put on these gammas in such a way that the moduli spaces of the surfaces on which we cut sigma are non-trivial. And then we have the superintegrable system given by these natural projections. So if it's a torus with one puncture, then it's just a kind of non-linear version of what I was explaining as a Kalogero-Moser system. So the mapping class group acts on this symplectic manifolds, gives lots of interesting equivalences, and singularities of these systems, they're very interesting. There is a recent paper by Dallin and Feher. Just for the torus, it's already quite non-trivial. So the quantization gives Berlin spaces, and superintegrable system gives McDonald types operators and the symmetries. That's started in our paper from last year. Thank you.
Okay, are there any questions?
Thank you for the talk. So in this last part, is there a Bohr-Sommerfeld kind of count of the dimensions that appear in the geometric quantization given the superintegrable system?
Yes, of course. And it's a very interesting question. So this quantization can be done geometrically through geometric quantization, and then of course there will be all these interesting problems. Or you can do it algebraically. Just first, in some sense, it's you can present a quantum system, and then you do dequantization, semi-classical limit. So I know the answer when you do it in the second way. Geometrically quantizing with Bohr-Sommerfeld type conditions. It's an interesting problem, but I think it's unsolved.
Okay, are there any other questions? If not, let's thank Professor Rich.
Hello, Professor Wang. Can you hear us?
Yes. Can you hear me?
Wait a minute.
Yeah, hi, Wotao.
Oh, hi. Hi, Weidong.
Hi, Weidong. So, you ready, Wotao?
Yeah, I'm ready.
Okay. All right. Our next talk is Professor Mutao Wan from Columbia University, and he'll be speaking on calibrating forms for minimal graph in arbitrary codimension. So let's welcome Mutao.
Okay, thank you. Thanks for the introduction. It's a great pleasure and honor to speak at this occasion, celebrating Leon Simon's 80th birthday and the proof of the Calabi conjecture and the Uhlenbeck-Yau theorem. So I want to talk about this new work about calibrating forms. So let me start with a brief abstract of this work. So we actually introduce a family of closed differential forms, and they're associated with minima graphical submanifolds in Euclidean space. So that's what the minima graph referred to in the title. And the point is that these are minima graphs of arbitrary codimension. So for each minima graph, we actually construct an explicit closed form such that their restriction agree with the induced volume form. And this actually admits a geometric interpretation as the pullback of tautological form on the Grassmannian via the Gauss map. So this is submanifold theory. So we actually construct the tautological form on the Grassmannian, and then we can just pull back this form via the Gauss map. And this is the calibrating form that we have. So this calibration problem is just reduced to estimating these co-mass. And we identify conditions to ensure the co-mass is equal to 1. And then it follows that any minima graph satisfying these conditions is calibrated. And calibrated imply area minimizing. So I'll explain this in my talk. And as an application, we verify a conjecture of Lawson and Osman in arbitrary codimension under two dilation condition. So this is joint work with Chongrun Cai. And this is a plan of my talk. So I'll introduce a pre-calibrating form. For minima graph of any codimension. And I'll explain how you actually generalize the classical calibration form from the codimension 1 setting. So this is usually the, sort of the first theory you learned in a minimal surface theory. And in the codimension 2 case, I'll just write down this calibrating form explicitly. And I'll show how the closeness of this differential form follow from the equation, and show that how you actually reduce to restrict to the volume form. And I also explain in this codimension 2 case how the co-mass can be estimated, and show that these minima graph they are calibrated. Okay, so let me just start with the definition of what minima graph mean in my title. So they're just very simple. So a submanifold in Euclidean space. Here I have n and m. So this is a minima graph of dimension n and codimension m. If it's a graph of such a map, so omega is just a domain in Rn. So you have Rn here and Rm here, and there's a domain omega, and the graph of this map, if it's actually minima. So the point is that sigma is minima. So minima here simply means that its mean curvature vanishes. So this is what we refer to as a minima graph of dimension n and codimension m. And being minima means that it's actually a critical point of the volume functional. Okay, so you derive the Euler-Lagrange equation for the volume, and it's a critical point. And of course, a very natural question is whether sigma is actually area minimizing. Okay, so it's a critical point, but whether it's a local minima. So for example, you can ask this question in its homology class. And this turned out to be true if the codimension is 1. Okay, so if this m here is equal to 1. And this is well known, but let me just go through this very quickly. So let's just look at the simplest case. When you actually have the graph of a function, so it's a scalar function codimension 1, defined on R2. So we can just take the coordinates. So this is x, y here, this is center, and the coordinate of z here. So suppose sigma is a minima graph, and then we know this is the area functional, and this is what you learn in multi. And then you can derive the Euler-Lagrange equation, and this is what we call the minimal surface equation. Okay, so this is one of the most fundamental nonlinear elliptic equations. It's a second-order elliptic equation for f. But in this case, you can actually construct a two form. Okay, this is omega, this two form here. Okay, and this star here is just the Hodge star on R2. So df is just a one form on R2, and you can form this this form here. And the claim is that sigma is actually calibrated by this two form here. So this means the following: while d omega is equal to 0, this is a closed form. And the restriction of omega to the graph, to the sigma here, is actually the same as the volume form. And thirdly, the co-mass of omega is equal to 1. So I'll explain what co-mass mean in the next slide. But all these together imply that sigma is area minimizing. And you can see that this d omega equation really just from this this minimal surface equation. Because when you take the d of this omega here, the d of the first part vanishes because they're, this is these are two forms on R2. But the last part here, when you apply d, the vanishing will just correspond to the minimal surface equation. So the closeness of this this calibrating form is exactly the minimal surface equation. And let me just recall what a calibration mean or what calibrating form. So calibration or calibrating form. So an M form is a calibration or a calibrating form. If first of all it's closed, d omega is equal to 0. And secondly, the co-mass of this M form is equal to 1. This means that if you take this this differential form and you pair with any oriented M-planes in this or in our ambient Euclidean space, and then the soup is always less than or equal to 1. Okay, so this is what I mean by co-mass is equal to 1. And then let's also recall this definition of calibration. So the n-dimensional submanifold is calibrated by calibration. This is M form referred here. If the restriction of this M form is exactly the volume form of this this submanifold. And then let me just give you this this is a one-line proof of this area minimizing problem. Namely, if sigma is calibrated, you recall this calibration, and the restriction of the volume form is it gives the volume form. So calibrated actually imply area minimizing, and this is an area minimizing in the same homology class. So suppose you have a sigma prime that is in the same homological class as sigma. Then, here this is we have several equality inequality. So the first one, just use the fact that the co-mass of omega is less than or equal to 1. So this is equal to 1. So this is use co-mass of omega is equal to 1. So the soup is less than or equal to 1. And this equality is due to the fact that they're in the same homology class. And the third equality is because the restriction of omega is the volume form of sigma. So you can see that if they're in the same homology class, then the volume of sigma prime is always greater than or equal to the volume of sigma. So sigma is actually area minimizing. So this is actually the most effective way to show that minimal submanifold is area minimizing. Okay, and let's just recall some standard calibration. So for example, the standard Kähler form on Cn, okay, and we know that this is what is called a vertical inequality, that any complex submanifold of Cn is calibrated by appropriate power of omega. So it's if it's 2k, then it's a real dimension is 2k, then this is calibrated by omega to the power k. And also the holomorphic N0 form on Cn, okay. So this is the holomorphic N0 form on Cn. So this is the case when you consider Cn as a Calabi-Yau, and then a special Lagrangian submanifold is calibrated by this this form here. And this one observation here, you can see that these two calibration forms, they're actually parallel, or they're actually of constant coefficient. Okay, so they're independent of the submanifold. They're actually calibrating. But the codimension one case we just mentioned, So let me just show you this codimension one. So this is a form. So you can see that this construction of this this codimension one case actually depend on sigma. So F is the defining map of the graph. Okay, and the closeness actually is actually essentially equivalent to the equation. So this is observation. So these calibration forms, they're actually parallel, but the codimension one case is not. So codimension one, so you can say the calibrating form is actually tailored for the submanifold. And we're interested in this question whether in higher codimension case you still have area minimizing. So this question is that what about higher codimensional minima graphs? So we know in codimension one they're always area minimizing by this calibration argument. And we have a positive result. This is a theorem of Lawler and Morgan. I tell you that if you have any smooth minima submanifold of the Euclidean space, then it's always locally area minimizing. So it means that at any point you can find a neighborhood where it's actually area minimizing in this neighborhood. However, the global picture is different. So higher codimensional minima graphs, they actually can fail to be area minimizing globally. Yeah, these are examples that were constructed by Osserman, and they were actually and then by a theorem of Mikolev later. Then you can show that these examples, so they're actually sigma 2 in R4. So they're two-dimensional minimal surface, and they're actually entire minima graph over R2. So they're actually a graph defined on R2, and it's defined on entire solution. Okay. But they are not area minimizing. Okay. And therefore, you can see now this actually calls for an effective criteria for calibration. So we know it's locally, but can we actually find an effective calibration criteria for the submanifold to be area minimizing? And our work is about such a criteria. So this is a theorem proof with Chong and Chai. So we proved that for any minima graph, there exists an M form. This is theta here, such that d theta is 0, so it's closed, and theta is restricted to the volume form. And the comass of this theta here, this is not always less than or equal to 1. But we show that it's actually bounded by a constant that depend only on the two dilation of the defining map. So if sigma is actually a minima graph here, so this is a defining map F here. So this defining map is from domain in Rn to Rm. Then we can take a differential. This is a linear map. And then this wedge 2 of df is just the induced map on wedge 2 of Rn to wedge 2 of Rm. Then we can just take the sup norm of this. Then we show that the comass actually is bounded by this. And therefore, you can see that once we can control this bound here, then we can get a calibrating form. And it turns out there's actually a very clean condition for the comass to be equal to 1. Okay, so this is a codimension 2 case. So if you have a map here that is from a domain in Rn to R2, this codimension, this M here is equal to 2. And if this map is error decreasing, namely this two dilation is less than or equal to 1. Okay, this is simply a very geometric condition. It means that if you just take any two-dimensional subspace here, then the area of the image is going to be less than the image of the area of the domain. So you always contract a two-dimensional area. So as long as this condition is satisfied, then the associated differential form will satisfy comass is actually always equal to 1. And therefore, a corollary of this one here is that, well, if you have a codimension 2 minima graph, and if this map here is area decreasing, then this is always area minimizing. So this is what we refer to as the effective criteria for area minimizing. And we do have theorems in general codimension, but let me just first talk about the construction of this calibrating from this data here. So as I mentioned in the beginning, it actually came from the Gauss map. So here in general, if you just consider a minimal submanifold, so n dimension in Rn plus m, then we can consider the Gauss map. It's just going to send the point on sigma to the tangent space as a point in the Grassmannian. So this is Gn n plus m. This is the Grassmannian of oriented n planes in Rn plus m. So the Gauss map, I mean, the codimension 1 case, it's really just a unit normal, and the Grassmannian is just a unit sphere. But if sigma here is graphical over Rm, then we can construct this form here via the pullback of a tautological n form, T on the Grassmannian. This means that at any point, so each point on the Grassmannian is an n-dimensional subspace. And to each n-dimensional subspace, we actually associate an n form. Okay, and then this data here can just be interpreted as the pullback of this tautological n form through the Gauss map here. And to define this data here, we actually need to first define a map here. So let's just look at a point on the Grassmannian. So this will correspond to an n-dimensional oriented subspace of Rn plus m. And we assume that L is a graph of a linear map from Rn to Rm. So this is the case, Rn is here, Rm is here, and L is the graph of this map. So this map is what we call FL. So this is a map from Rn to Rm, and L is the graph. And we first define another map. This is a JL map. Now this is a map from this L to L perp. L perp is the orthogonal complement of L here. Okay, and this is defined in the following way. So we first define an isometry from Rn to L. Okay, so this Rn and L, and you can check that this map here, we actually define an isometry canonically. And then because it's graphical, you can also define an isometry from Rm to the orthogonal complement. And this JL map. JL is one that maps L to this orthogonal complement. It's just defined so that the following diagram commutes. So this is the isometry. This is also the isometry that identify Rn with L and also Rm with L perp. But we already have we start with a map FL here from Rn to Rm. So this is really just a commutative. So it's really just going like this. And once we have this JL here, this is from this L to L perp. Then we can actually construct this. This is basically an operation on M forms. So given an M form here, we can define an M form using this JL. So this is defined the following way. So we fix an orthonormal basis, E1 up to En of L. Then we set this psi phi to be equal to this. So we apply JL to each one of them. And then this is a vector, but we put a flat here that will become a one form. And then this I here is the interior product. So if this is an M form, and this interior product will be an M minus 1 form, and then you wedge with the M form. So this is an operation on M form. And you can check that this is actually independent of the choice of the basis. And then we define our iteration. So you can see that this is basically the volume form of L. But now we define this by iteration. We iterate by L here. And then this form data is just given by this power series of this iteration here. Okay, so you can see that this is defined for each point on the Grassmannian. Well, as long as it's graphical, then we can define this JL here, and then this is just defined at any point. But once we have a Gauss map, then we can use this Gauss map to pull it back. So this looks quite complicated, but let me just write down what it is in the codimension 2 case. We're actually surprised by the simplicity. Okay, so this is a codimension 2 case. Okay, this is m is equal to 2. So we're looking for a map from a domain in Rn to R2. So let's assume the two components are f and g. So they're just functions defined on Rn. And you can easily write down the volume of f. Okay, so it's given by this formula. And you can easily check, for example, if g is equal to a constant, then this is just reduced to codimension 1 case. And of course, this quantity here is just the volume form. So we just define xi to be this one here. And then you can derive the Euler-Lagrange equation of this functional here, and you arrive at these two equations. And these two equations are, again, reminiscent of the codimension 1 case. So for example, if you set g is equal to 0, okay, if you set g is equal to 0, then if you set g is equal to a constant, then this equation here, again, just reduced to the codimension 1 case. But because now codimension is 2, so we get 2 equations. And then in this case, we can just write down this calibrating form, this theta here. Okay, so we just need to use coordinates on Rn and coordinates on R2. You recall this is a map from Rn to R2. So the submanifold is in Rn plus 2. And these are just the ambient coordinates. And in this case, if you just follow the procedure I just described, and you write down this data here, then it's actually of this form here. And again, you can check that this reduced to the codimension 1 construction. So for example, g is equal to constant, then this is a codimension 1 case. And you can see that this whole thing is actually symmetric with respect to f and g. And the interesting thing here is, well, once you have this data here, and if you check the closeness of this one here, then just similar to the codimension 1 case, the closeness of data. If you just check this one here, just apply d here, then you're going to see that it actually corresponds to exactly these 2 equations. And those are just the Euler-Lagrange equation of the volume functional. So that corresponds to these 2 parts. Okay. So this one here will actually correspond to this, because we have a hard start here. So this is just a generalization of codimension 2 case. We construct a form here, and the closeness of this form here just follow, or is actually equivalent to the equation. And you can actually check again, verify that the restriction of data is actually the volume form. Because in this case, once you're restricted to the graph, you really just need to set y1 is equal to f and y2 is equal to g. And then you carry out this whole calculation, you realize that this is actually true. So restrict to the volume form here. So in codimension 2 case, it's actually very simple, and you see it, and you know it generalized the two-dimensional. And once it has a property that this is a closed form, and it's also restricted to the volume form, then it suffices to estimate the co-mass. But this co-mass calculation is actually point-wise. Okay, you can see that this is a form here. So we can actually point-wise. So in this case, we can actually rotate these coordinates. So we can rotate the coordinates x1 up to xn and y1 and y2. So this will be equivalent to the singular value decomposition at each point. So if you rotate the coordinate, you can see df is equal to lambda 1 dx1 and dg is equal to lambda 2 dx2. and so that their gradient are perpendicular. And here, lambda 1, lambda 2 are just the singular value of df, okay? Because it's a pointwise calculation, so we can choose the coordinate such that it's in this form. And once you reduce this form here, then theta actually reduce essentially to a 2 form. But for 2 form here, it's actually it's much easier to calculate the co-mass, because you can really just take kk transpose, and then it's just going to be the square root of the largest eigenvalue of this. In this case, you can do this calculation, and then yeah, it just you can show that the co-mass of theta is less than or equal to 1, as long as this condition is satisfied. So, namely, the product of the 2 singular values is less than or equal to 1. But this is exactly the error decreasing condition. So, because this is exactly this is exactly this measurement we're talking about, df. Okay, and therefore the error decreasing condition just imply the co-mass is less than or equal to 1. Okay. So this is a codimension 2 case when you can actually write down everything very clearly. And but in general case, yeah, this is the case of general codimension m. Then in this case, you have m component. Okay. Then in this case, the equation is what we call the minima graph system. Okay, it really just corresponds to yeah, this each of this function is actually a harmonic function with respect to the induced metric. Yeah, so this GJK here is actually the induced metric on the graph. Okay, and this is the inverse, and G is the determinant. But this is actually a divergent system, yeah, on the graph. But if we just follow the construction of theta here, then we see that the d theta equal to 0 actually follow from this equation, just like the codimension 2 case. And you can also check that the restriction of the to the graph is exactly equal to the volume form by this minima graph system. And so in general codimension case, we also can estimate the co-mass. So our theorem is that so this is general codimension case when you have a domain in Rn, you map to Rm, and if it's a minimal submanifold. Then in the following 2 cases, we know that the co-mass theta is equal to 1. Well, the first case is actually the case rank df is less than or equal to 1. But this is really just correspond to the codimension 1 case. Because our condition, yeah, our condition was in terms of 2 dilation. But if you have a map whose rank is equal to less than or equal to 1, then the 2 dilation is always equal to 0. And if the rank is greater than or equal to 2, then the condition is actually in terms of the product of the any 2 singular values. So this is again a 2 dilation. And you can see that this is well, when R is exactly equal to 2, that's the codimension 2 case, and this is exactly equal to 1. So actually recover the previous theorem that I mentioned. And in either case, you can show that the co-mass is exactly equal to 1. And then and therefore, by the argument we just mentioned, the graph is calibrated by this calibrating form that we constructed, and therefore they're actually area minimizing. Okay, and let me just say a few words about this Lawson-Wasserman conjecture. Okay. So, well, this first of all, go back to the minima graph condition, namely the mean curvature is equal to 0. Okay, because for some manifold in Rn plus m, well, the equation corresponds to the mean curvature vanishes, but the mean curvature actually has m plus m equations because it's that vector in Rn plus m. So really, the minima graph condition actually correspond to the full system of m plus m equations. Okay. So this is the one we just talked about. but there are actually also the other n equation. And these actually correspond to, well, you're deriving the Euler-Lagrange equation for the submanifold. So you can do different kind of variation. This is actually correspond to a variation in the domain, and this correspond to a variation in the target. However, there's an argument of Lawson-Osman shows that if this F alpha here, they're actually C2. Wow. So yeah, then 2 actually imply 1. Okay, so if F alpha is C2, then you show 2 actually imply 1. But now if you look at this equation 2 here, you see that this 2 here can actually be defined weakly, because this is actually, again, this kind of divergence form. So you can actually define a weak solution of this alpha. So F alpha doesn't have to be C2 for this system to be well defined. So a conjecture of Lawson-Osman says the following. This is from 1977. Says that if this F alpha here, they're all locally Lipschitz. So if they're locally Lipschitz, then you can actually make sense of this equation weakly. I mean, just by integration against C infinity functions. So they conjecture that this property, namely 2 implies 1, not only is true for C2 functions, but they're also true for locally Lipschitz functions. So if 2 imply 1, then it means that these 2 are actually equivalent. Okay, so it suffices to just find Lipschitz solutions of this system here, and then it will imply the first equation, and we imply that's actually it's actually minima. So in other words, the graph of locally Lipschitz solutions of 2, they actually have vanishing first variations. Yeah. So once we have, so the strategy is that once we have a weak solution like this, then we can actually use this data that we just mentioned, to construct a weak differential form. Because once these Lipschitz, the theta form that we mentioned, they're still defined. They're still defined as L infinity norm. So you can still talk about this, and you can still apply this the calibration argument. Okay, and then you show that they're actually well, in fact, in this case, they're not only they not only have this they're also error minimizing, but then they certainly satisfy the regularity result. So in other words, the graph of locally Lipschitz solutions of 2, okay, they actually have vanishing first variation, and they're actually stationary variables in the sense of geometric major theory. Okay. So we were able to use this calibrating form to verify this the Lawson-Osman conjecture, but now this is true in all codimension under this 2 dilation condition. So lambda j lambda k is less than 1 over r minus 1 squared. So in particular, in codimension 2 case, this is the error decreasing condition. Okay, we actually have a different version of this bound here. That is actually linear. The denominator is linear in terms of the rank. And this conjecture, as far as we know, there is some partial form of the conjecture under some additional invariance condition by Dimler, and also Hirsch, Mooney, and Tioni. They proved this conjecture when the domain is 2-dimensional. Okay? But our result is about any codimension, but we do need this condition here. And at the end of my talk, I'd like to mention two related questions, because in particular related to this kind of error decreasing map. Okay. So the first one is about a Dirichlet problem for error decreasing minima graphs. So the question is the following: it's about just construct construct minimal surface system equation under this boundary condition and under Dirichlet boundary condition. Okay. So suppose f from omega in Rn to R2 is actually error decreasing map. So this is a condition I just mentioned. Then the question is that can you actually deform this f here via the mean curvature flow to an area decreasing minimal map with the same boundary. Okay, so this is you have a graph here, and you start with an initial condition here, but assuming the initial condition is area decreasing, and then you ask whether you can actually construct a minimal map. So and once you can construct one under this area decreasing condition, then by our theorem we know it's area minimizing. And the key issue here is actually the boundary estimate, because we already know this area decreasing condition is preserved under the mean curvature flow. This is one of the reasons why we want to use the flow approach to approach for this problem. As we in some earlier work, we can already show that if in the absence of boundary, then this area decreasing condition is actually preserved under the mean curvature flow. So as long as you can control the boundary regularity, then you can start with an area decreasing map, and you flow by the mean curvature flow. It's going to remain area decreasing, and if you can show that the flow converge to a point, and then this is going to be minimal, and it's area decreasing minimal map, and therefore it has to be area minimizing. And there are actually already some partial results earlier by myself, by Dingyao Xin, and some recent one by Li and Zhou. And another question here is that it's about the existence of entire minima graph of codimension 2. So this is actually related to this work of Bombieri, Di Giorgi, and Giusti. Okay? So Bombieri, Di Giorgi, and Giusti, they actually construct entire solutions of the minimal surface equation. So this is actually defined from Rn to R. Okay, so this is an entire minima graph over R8. Okay. But as I mentioned, in their case, the codimension is equal to 1. So this is R1. Okay, and this is the one that was blown down. Actually, is related to the well-known Simon's cone. So we can ask the following question: can you actually find the entire solution of the minima graph system such that the rank is actually greater than or equal to 1, because at some point, and also satisfy this this area decreasing condition? Okay, so because we know this condition is always satisfied if the rank is equal to 1. So in particular for Bombieri, Di Giorgi, and Giusti, we know this this condition is always satisfied. But that's also the codimension 1 case. So you can imagine you can take the Bombieri, Di Giorgi, Giusti example, just increase the trivial dimension. So you actually become codimension 2, although its rank is still equal to 1. But the question is that whether you can actually perturb this one here into a genuine codimension 2 entire minima graph. So genuine will refer to this rank. So you need the rank to be at least equal to at least greater than 1 at some point. And so that you also satisfy this area decreasing condition. Because the original one has this two dilation equal to 0. So we hope this will actually preserve. And if you can actually construct such a solution, then it's going to be area minimizing. So it's going to be globally area minimizing in codimension 2. And it's going to be, there are some entire minima graph in hierarchical dimension, but I think most of them are actually of this special holonomy type. And this will be a new example. Okay, so I think my time is up, so I'll just stop here. Thank you.
Are there any questions?
Can you do a similar calculation if you have a codimension 2 submanifold and a graph over this codimension 2 submanifold? So in other words, it's a section of the normal bundle.
You mean the base is going to be a general Riemannian manifold, or?
Yeah. It's a codimension 2 submanifold in a Riemann manifold. Then you take graph of this guy.
Yeah,
So
it's yeah.
can calculation for that?
Well, you still have this first order system of the differential. I mean, this structure is still there because this is Euler law, and then we can still rewrite. But there are actually curvature forms there that we still don't know how to deal with. I mean, there's not a clean formula at this point.
Well, simpler case is take a complex submanifold hypersurface in another Kähler manifold, so it's codimension 2.
Yeah.
And you write over here. Wow.
So you have a complex hypersurface in another.
Yeah.
And you take the normal bundle of it.
Yeah, to deform it in the normal bundle.
Yeah, this is a yeah. It just as I said. I mean, the curve. We're still not quite sure about the curvature contribution. I mean, in this case, I mean you yeah. When after the D, there are actually the not only the ambient curvature, but the Gauss-Codazzi equation of the submanifold will actually come in. And well, you can still construct this tautological unfold, but this is going to be a section of the Grassmannian bundle. So yeah, it's just again how to interpret those terms.
Hi, Mutal. It's Rick. So,
Yeah, Rick.
let's see. I had actually two questions. So there's a kind of special class of minimal graphs in high codimension, which I think you've also looked at, which are graphs of diffeomorphisms. So is there anything special about, let's say you took a diffeomorphism of a two-dimensional domain to a two-dimensional domain and its graph is minimal. Is there any possibility that such a graph would be area minimizing automatically?
Not in this context. I think in our context, sort of you have to sort of favor one direction. I mean, favor the domain. I mean, it's a diffeomorphism. Yeah, well, it's a diffeomorphism. I guess the thing you have is the Jacobian is always positive. No, I don't know. I don't know how whether this can enter this condition. Yeah.
Okay, so the second question is, did you earlier prove that under this condition, the submanifold is stable?
Yeah,
Is there,
yeah, right. We had some
Okay.
earlier condition. I mean, we show that this is stable, but now this is area minimizing. Yeah.
Right. Do you expect that there might be a more flexible condition which implies stability but not area minimizing?
Well, the methods are actually quite different. Yeah, but I mean, we're hoping that this will actually maybe provide some insight of rewriting the stability inequality. I think in higher codimension case, yeah, the method that we employed in improving the stability theory involving a particular form of rewriting the stability inequality, which is actually not optimal. But we're hoping maybe this will help us to rewrite the stability inequality in a nicer way, and maybe the distinction between stability and area minimizing could actually come out. But I don't know at this point. Yeah.
Okay, well, thank you.
Sure. Yeah.
Are there any other questions?
Okay, Professor Wang, I got a question. So I'm wondering if the two dilation condition can be, can be given a more geometric formulation. For example, as an angle condition or convexity condition on the Grassmannian. Thank you very much.
Yeah, you can. I mean, this is actually well, you can actually interpret this condition in terms of Grassmannian geometry. In fact, I mean, I think this is it corresponds to a convex region, and this is why the mean curvature flow will actually preserve this condition. I mean, you can interpret everything in terms of gross Montian geometry.
Okay, thank you.
Okay, are there any? So if not, let's thank Muta again.
Okay, thank you. Yeah.
Are you coming to China in the summer?
Oh, he's gone. Okay, we'll be taking 10 minutes break and back for the third lecture.
Well, I'll be in this contest.
Oh, okay. Well, come to Beijing.
Yeah, that I think 20 end of June. Yeah.
Good.
Yeah.
All right,
Okay.
thank you.
Yeah, thank you.
Bye bye.一二三。
It's already.
Yeah.
Yeah. Okay.
Okay, we'll continue our third talk in the morning, and the will be given by Professor Kenji Fukaya of YMSC, and his title is Q structure, Galois symmetry, cyclic symmetry in open closed Lagrangian floor theory. That's well.
Yeah. Thank you very much for introductions. And I'm very happy to talk in this conference. And I think I have to apologize that the title is not so much related to geometric analysis. Actually, I have been working on geometric analysis for a long time and I know, I think I know and I like nonlinear PDE much more than Galois group. And when I got this invitation, I was very happy, but then I didn't check the topic of the conference so much. I just sent the title, which I have been working on in this couple of months. So, but yeah, anyway, so this is something I'm supposed. So now let me start by something in algebraic geometry. I'm not expert of algebraic geometry, so don't worry, I don't talk so much difficult thing. So let X be a projective algebraic geometry, a smooth projective algebraic variety defined over Q. It's just some solution of some homogeneous polynomial with rational coefficients. And we consider it a category of coherent sheaves on X and its derived category. And there is a notion of coherent sheaf over defined over Q. So it's This old version, I suppose. New one yesterday, this morning. I have this one. If you just connect it, I can use it. I hope this is new one. Yeah. This one new. Yeah. Okay. Not very different kind, but let me okay, continue. Yeah. Yeah. It's okay. Yeah. So we consider this category of coherence shift over X, and we say that not all objects of them are defined over Q. And this, since I'm not expert, I just explain very elementary things. So we just consider X is just a P1. It's complex number plus point infinity, and we take some complex number, and there is something called a skyscraper shift f of z. It's the following: if you have any open set which contain z, then this section is complex numbers, and if it doesn't contain z, then the section is 0. So just rank one thing on z and everything else. And you can explain that this, you can expect that this shift is defined over Q if this point z is a rational number. So that's what this shift defined over Q means. Okay, so now we consider this category coherence shift on X. And there are some object which is not defined over Q. So we take some F. It's a finite Galois extension of Q. It's some field contained in C, and it's a finite extension of Q, and Galois extension is normal. And we consider this subcategory so that its object is defined over F. So in the case of skyscraper shift, we just consider the point Z, which is an element of this field F. And so now this Galois group acts on these categories. For example, in the case of skyscraper shift, then if Z is the element of F, then the Galois group just permute this point of F. So you have this actions. So what does action do? So you have any shift which is defined over F, and if it's a Galois group, and if you have any object of this shift, it's a coherent shift where it's a chain complex, then you can transform this object by this Galois group. You have another shift. So this Galois group acts on this category. And moreover, if you consider the space of morphism between two objects, it is actually a shift cohomology of the home shift. And then the shift cohomology is also acted by this Galois group. So this is originally a vector space over F, this finite extension of Q. And then this Galois group kind of sends a linear map from this morphism space from C prime to C sigma to C prime sigma is cohomologies. And this C sigma is not F linear, but it's a twisted F linear. It means that you have an element of F A and element of morphism shift cohomology. The sigma star AF is just you transform A by this Galois group and sigma star X. This is very simple things. So you have this. So this is what I mean by this category is defined over F, and it's in kind of Galois group act on this category. Okay, so now we consider something called a Hochschild homology of this category. It's a thing like that. You take this K object, you take some morphism, shift cohomology from C0 to C1, blah, 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 CK to C0, so it's coming back. You can just imagine like this. So x0 here is a morphism from C0 to C1, and x1 from C1 to C2, and blah, blah, blah. And you come back, and xk is a morphism from ck to C0. So this is this kind of tensor product, and you move all the C0 to ck. This is Hochschild homology. And the Hochschild boundary is just defined something like this. You have 3 tensor product. You just kind of remove this tensor, just replace it by the multiplications, x0, x1, x1, x2, and x2, x0. So this third term is typically Hochschild homology. And of course, you have differentials. You can just take differentials. And what what easy to observe is that this Hochschild cohomology or Hochschild chain complex is acted by this Galois group. So first of all, this is a F vector space, but the Galois group acts on this Hochschild homology because all this object and all this morphism are just acted by this Galois group. So this big vector space and big chain complex is a Galois group actions. It is twisted linear. Then we just take its set of invariant of this G actions. And this is by definition of Hochschild homology over Q. So not all object is defined over Q, but you just take all the objects. You have a Galois group action. You can define this Q Hochschild homology over Q. So this means that you have any X, which is a projective algebraic variety defined over rational numbers. Then you can use this object, which is defined on the number field, and its morphism to define Hochschild homology over Q. Now, there is some map called the Hochschild constant Rosenberg homomorphism, which is isomorphism between this Hochschild homology and some of the piece cohomology of the Q forms. So this Q form is a holomorphic Q form. So you consider this vector bundle of Q's holomorphic differentials, and then you take its piece sheaf cohomology, and you take P and Q, sum up. This is a Hochschild homology, and it is known that this is isomorphic to this Hochschild homology of derived category of coherence sheaf. And in an affine analog, this is a following thing. So you take this ring. So Q is, so you take polynomial ring and you divide it by ideal. So this is a kind of ring of polynomial functions on our affine algebraic variety over Q. Then the Hochschild homology of this is just given by this K plus 1 tensor product of the element of this ring. Then this Xi is a polynomial modulo some ideal. So you can just associate to this thing x0 dx1 wedge blah 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 dxk. So this is a K form, and this is actually a special original case. This Hochschild constant Rosenberg discovered. So you have this Hochschild homology, and this is a H0 of omega q. And of course, in affine case, there is no higher. So this is a case of affine case of this Hochschild constant Rosenberg homomorphism, and you can globalize to get some similar homomorphism from projective algebraic variety, and then you can just categorify so that replace this coordinate ring by this derived category coherence sheaf. So this is some important isomorphism in non-commutative geometry or this kind of algebraic geometry. So now let me consider this isomorphism, and it is kind of rather easy that if an X is algebraic variety defined over Q, then this isomorphism is an isomorphism over rational number. So originally it is just complex numbers, but it is an isomorphism over rational number. So what is a Q vector space structure of this cohomology? So HP of X omega Q, and omega Q is of course a vector bundle, and in a case when X is algebraic variety over Q, this vector bundle is also defined over Q, right? You have a natural notion of vector bundle over Q. So then you just define this Hochschild this sheaf cohomology using in the usual algebraic geometric way, Zariski topology over Q, then everything is defined over Q. So that is a Q structure on this right-hand side. And the left-hand side, as I say, that derived categories, you can take a finite number field and take fixed Galois group action. So it is a Q vector space. And this isomorphism is actually a Q isomorphism. You can just see from this, right? This map is basically Q, is defined over rational numbers. So this is the Q isomorphism. So So this is kind of so this constant Rosenberg isomorphism is Q homomorphism, and the meaning of this non-commutative geometry is just people kind of regard this kind of category as a kind of analog of spaces. So in place of considering spaces, you can just consider some category. That's something like a non-commutative object. And if you want to define, if you want to take analogy of the cohomology of the spaces, this Hochschild homology of the category is just analog of the cohomology. And then this isomorphism shows that, okay, we can just describe category coherency of X as just a replacement of X. And the cohomology theory is like this. And this just says that this story works over rational numbers. So now, on the other hand, of course, you know that this sum of the holomorphic Q form vector bundle, piece form of holomorphic Q vector bundle, this sum is just the ordinary cohomology of X over complex numbers. This is the Hodge decomposition of the cohomology using PQ forms. So this uses a lot of transcendental structures. So this is Hodge theory. But then we consider this cohomology and it has another Q structure because if you look this so you look this side, then of course H star XC is a tensor C of the H star XQ. So it has a Q structure. And what's rather well-known thing is that this cohomology ring has a two different Q structure. One is a Q structure which came from this side. So HPX omega Q is a Q vector space. So its direct sum has a Q vector space, structure of Q vector spaces. On the other hand, of course, H star XC is a Q vector spaces. So it has a two Q structure. One is called algebraic Q structure is this guy. And this is comes from the fact this omega Q is a vector bundle defined over Q. And there is some other structure called a transcendental Q structure. This just came from the fact that the space X is actually a topological space or a manifold. And you have these two Q structures, and this two Q structures is definitely different. Because, of course, in the usual cohomology theory, this HPX omega Q is not a Q vector subspace. Its complex conjugate is HQ omega P. So Hodge structure, this decomposition is not a decomposition of a rational number. So this Hodge cohomology, algebraic Q structure is very much different from this transcendental Q structures. And this is very much a famous and well-known fact. And the difference of these two Q structure is actually very important in Hodge theory. So the difference is very important part of the Hodge theory. I just want to explain very simple example. Maybe it's not so easy. It's classical. So you take T2, it's an elliptic curve. It's just a y square of some third order polynomial with rational coefficients. And then in an elliptic curve, you consider this zeroth cohomology of omega 1. It is a holomorphic one form. So on this elliptic curve, we have a dg of holomorphic function. It's holomorphic one form. And since this is rank 1, so this is a Q basis of our algebraic Q structures. Then I want to see this algebraic Q structure using this transcendental Q structures. So to see the transcendental Q structures, we take this 2S1 here, gamma 1 and gamma 2, which is a cycle on T2 generating this H1 of Z. Then you take integrations of this holomorphic one form on this gamma 1 and gamma 2. Then this gives how this holomorphic one form Q basis on algebraic Q structure looks like in the transcendental Q structures. And of course, this is a famous object. It's a kind of period of elliptic integral associated to this elliptic curve. And of course, the ratio of these two guys is never rational number. It's a transcendental number in general, even if the algebraic curve is rational. So understanding this period is very much an important part of the study of elliptic curve. It's very classical. And so the difference of these two Q structure is just understood using this period integral or vice versa. So understanding this period integral is one of the main purposes of the Hodge theory, but it is related to this difference of these two Q structures. So let me repeat. So you have this, usually this cohomology has two Q structures. One is algebraic Q structures and the other is transcendental Q structures, how they are related. And this two Q structures actually also recently discussed much in a study of mirror symmetry. like Ritani or Konsevich and his collaborators study like some gamma conjecture, blah, blah, blah. So they study this kind of relations of these two different Q structures. And that's the kind one of important topics in mirror symmetry. So now, what I want to explain today is the following things. So I want to say that there is some symplectic analog of the stories. I just say that in algebraic side, the story is that you consider this category of coherent sheaf, which is defined over Q. And this category of coherent sheaf, its Hochschild homology, describes this algebraic Q structure of your project algebraic variety X. But then I want to do some in a symplectic side. We have this category of Lagrangian submanifold, which called the square category, and we consider its derived version. And and the main thing I want to explain is that this category actually has a Q structure in a similar sense I just explained. And then you have this something similar to this Hochschild constant Rosenberg homomorphism. And this Hochschild homology is actually related to transcendental Q structure. So let me do it a bit. Yeah. So we take this isomorphism. And this, so the Q linear with respect to this algebraic Q structure, this is the Q linear. And how I want to explain is that this category, category of X has a Q structure, and Hochschild homology is a Q vector space. And this map, which is called the open closed map, will have this Hochschild homology to the ordinary homology or cohomology is actually Q linear. But this is Q linear with respect to transcendental Q structure on X. And this is, of course, because this X is just a symplectic manifold. So this story works for any symplectic manifold. So there is no algebraic Q structure. So this algebraic Q structure is somehow in a sense of topology much more delicate thing, because we use the fact that X is a algebraic variety over Q. So we use this very special property of X to define second Q structure. But transcendental is just for the geometry, it's very natural, right? It's just the usual Q structure and cohomology. And what I want to, so the main thing is just this, the category coherent sheaf is related to this algebraic Q structure. And symplectic geometry and Lagrangian player theory is related to this transcendental Q structure. So that's something I want to explain. And then this is related to mirror symmetry. So what mirror symmetry says that you have a symplectic manifold, you have this mirror complex manifold. I don't say so much, but in general, you may need some holomorphic functions on this complex manifold. But yeah, and what mirror symmetry predicts, it's conservative homological mirror symmetry, is that this category of this Lagrangian submanifold on X, this is object of the Lagrangian submanifold, and the morphism is player homology. And this category is actually expected to be equivalent to derived category coherent sheaf of X check. So this category equivalence is expected. So what happens on this? So then suppose that this Hochschild homology, then the Hochschild homology is isomorphic to the Hochschild homology of derived category, and this constant Rosenberg homomorphism just give this Hochschild homology is this Hodge homology, and this open closed map in many cases predicts that this Hochschild homology is actually isomorphic to the ordinal homology of X. And so maybe let us assume that this homological mirror symmetry works over rational number. Then this side, so then this guy and this guy are both Q vector spaces, and that is expected to be isomorphic. And then if you expect this two, so you have this two Q structures, but then this transcendental Q structure became this algebraic Q structure. So I think homological mirror symmetry, if proved over rational number, implies that the transcendental Q structure on your manifold just became algebraic Q structure on its mirror. So that's something I think very interesting to understand. I believe this kind of isomorphism is known, is already expected from very early stage of mirror symmetry. But I never heard so much how this isomorph is related to this homological mirror symmetry things. So that's the main thing I want to explain. I want to talk. So, but then I want to explain this. What is this category of category of Lagrangian submanifold? And also, this is something called the infinity category. And first, I want to explain what this what it means that this category is defined of is Q linear. So what it means? So the object of this category is a Lagrangian submanifold. It's a half-dimensional submanifold of a manifold X, so that the symplectic form vanishes. Then morphism space is called Freer homology, discovered by Freer, and it's a chain complex, and it's chain complex is a free vector space. Maybe I use Q today. It generated by the intersection points. So it's Q vector space. And what is the boundary operator? Boundary operator is something. So you have a P and Q intersection point, and you count the strip. So you count how many strips there are. This is Freer's boundary operator. That's the definition by Freer. But then, you know, I say that we count a number of the disks. And of course, a number maybe in a most naive sense is just an integer. But actually, there is some automorphism. So you count something, but you count something which has some kind of automorphism. Then the counting is a bit, you have to count a bit carefully. If there are some geometric objects which has a automorphism of order k, they'll be counted as 1 over k, not 1. So the count is not actually an integer, but it's anyway, it is a rational number. So this count is a rational number, but then it still looks like all the structures defined for Freer homology is just a rational number. So everything is Q linear. So the claim I just mentioned that the category is defined over Q looks too much trivial to explain. But actually, there is something we need to do. And actually, I could define these Q structures in the category, especially with cyclic symmetry, rather recently. So it takes much time. So yeah. However, actually, we need to generalize the story a bit so that the story is more kind of non-trivial. So I just want to explain why. So let me explain one simple example, why we need generalizations. You take this X, which is the one-point blow-up of two-dimensional complex projective spaces. And we take its scalar structure so that the first Chern class is proportional to this scalar form. This is, I think, Einstein. And I think this is Tian Liao who proved the Einstein existence of this scalar form. Pardon? It's not Einstein?
But not invariant now.
Oh, really? I don't know. Yeah, so,
3 or more.
okay, yeah, but this is true, right? I'm sorry, yeah. So it's not Einstein. It is monotone. It's not Einstein. I'm sorry. Yeah, I'm sorry. I'm very. I'm very. Yeah. Complex geometry is not so much. I don't know. Thank you very much for the corrections. But it is. We forgot simple complex structure. So symplectically it is monotone. But then there is a claim, so that if we have any two Lagrangian submanifold on X, and so that Freer homology is defined, and if we use this naive count as a definition of Freer homology, then the Freer homology is always 0. And I think I could prove it now. But we use some rather difficult theorem we just recently proved with Abusai or Ono. But this is not so much happy claim, because we spend several thousand pages to write definitions and to prove the theorems. But then conclusion is that okay, in this interesting example, everything is 0. So it's not so happy. So we have to. So it's always 0 is a bit too much bad. So I want to twist this theory so that you have something non-trivial in this very kind of naive examples. So this is a notion called Boundenko chain, which I developed with Ota and Ono. So we use this odd-dimensional cohomology class of your Lagrangian submanifold to deform your simplex structure, to deform your Freer homology. And this is a kind of something which satisfies this Molar-Cartan equations. And but maybe yeah. So in our case, dimension is 2. This is just a first order cohomology. So you may just think it's a one form. So it's a connections. And this Molar-Cartan equation in this case is just dB plus B wedge B is 0, because M1 first operation is just a drum differential, second operation is a wedge product, and all others are 0 in this very simplified cases. Then of course this is original Molar-Cartan's equations. That means that this closed one form is just a flat connections. So it means that in this cases, you just deform your cohomology by flat connections, and of course you know what it means. So it's a flat connections. Then we change this drum differential to this D plus B wedge. So it's a kind of cohomology of this flat vector bundle. So you twist usual cohomology group to this flat vector bundle cohomology group, and then you further twist you further kind of add some effect of holomorphic disks. You have this Lagrange submanifold. You count how many disks which bound it, and this gives some kind of so-called quantum corrections or instanton corrections to the usual cohomology. So that's what you get, this Fourier homology. So that's basically what Fourier homology do. But we twist it by using flat connections on this Lagrange submanifold. So now let us go back to the case of example. So let us consider this 1-point blow up of X. And this guy is a toric manifold, and it has T2 actions on this manifold. And this guy has and all orbit is a minimal. It's a kind of monotone, no, minimal, special Lagrangian. This is a kind of a particular case of SYG vibrations. And then there is one special orbit, which is called a monotone Lagrangian tori. That's something like two characteristic. One is this area, and the other is something called a Maslov index. That's something like a relative version of CAM class. So it's very similar to monotone conditions. Exactly one this monotone tori. And there's a claim, there's exactly 4 flat connections on T2, so that this Fourier homology is non-trivial if you twist by this flat connections. And this is, I think, I proved with Ota Ono something more than 15 years ago. So there is some particular 4 connections, and I want to make a bit more precise. So to make a bit more precise, so we consider this holonomy representations associated to these connections. You have a pi 1 of Z2 to this non-zero complex number. That's the holonomy representations. Then we take this generator 1, 0, and 0, 1. So you have these 2 non-zero complex numbers, y1 and y2, these are holonomies. And we use this y1 and y2 as a coordinate of the space of flat connections. Then the claim is that this y1 and this Fourier homology is non-zero if and only if y1, y2 is the critical point of this particular functions w. It's y1 plus y2 plus 1 over y1, y2 plus 1 over y2. And this function is defined by some counting some holomorphic disks, but I don't explain what you have this particular functions, so that it is vanishing is Fourier homology is related to the criticality of these functions. And so now we just try to calculate this equation. Differential of w is 0, and this is very easy calculations. You can do it in 10 minutes. And then the solution is that y2 is 1 minus 2, and you have this fourth order polynomial equations. y1 fourth plus y2 third minus 1 is 0. So this is, I think, irreducible polynomial of degree 4. So you have 4 solutions that correspond to this non-trivial Fourier homology. And you can easily see that this 1 is not a solution. It means that if you do not kind of include this flat bundles, then it is not critical. So there's no Fourier homology. It's all 0. So then if you look this equation, so this is irreducible polynomials. So the solution is actually not rational number. It's a kind of element of some number field, which is a degree 4 extension of the rational numbers. So so I want to define the notion that this bounding continuum connection is defined over some number field F. It's very natural and easy. So you just take holonomy representations. It goes from pi 1 to this complex numbers, and its image is contained in this number field. Then we call this B is defined over this field F. And actually we need to, so this is an easy case, but we need to include this odd cohomology, so higher order cohomology. And actually to work in a case when everything is not monotone, we need to use this Novikov ring, which is a formal power series ring with respect to this parameter T. And this BI is just a complex numbers, but we assume similar condition for this coefficient so that this this more generalized sense of bounding cochain is defined over some number field. So we can just define that kind of notions in a very natural ways. So now in these cases, so there are 4 flat connections, which is non-zero, has non-zero Fourier homology. And the holonomy is this y1 and y2. And it is the critical point of this particular Lorentz polynomials, superpotentials. And so there is a, so then I'm sorry. Yeah, so we take this field F, which is a solution of this order 4 polynomials. And exactly this 4 flat connection B is defined over this number field F. So that's what we observed. And actually we can prove that for any something called a toric manifold, we consider this Tn orbit, and we consider its Fourier homology. And we have this, we proved that there is finitely many pair of Lagrangian submanifold and flat connections, so that Fourier homology is non-zero. And using the proof, we can just see that all these solutions is just defined over some number fields, some finite extension of Q. So for toric manifold, you have plenty of examples that you have some object which is defined over number field, not over Q, but over number field and non-trivial Fourier homology. So that gives a lot of examples. And actually, with Ono, I did this kind of calculations more than 15 years ago. And this Galois group type things we observed that time. But we wrote it in a paper when we published it just as a remark, because the reason is that we cook up general theory for this Fourier theory, but that time the general theory is cooked up only over real numbers. So we use Ram's theory, we use only real numbers. So this is just a remark because we calculated, and it happened to be some number fields, element of number field, but this is not so much rigorous background. It's just an example of calculations. And we cannot say that so much about it. So we wrote it as a remark, but we have to work hard to make everything works over kind of rational number so that this is become real mathematics. Now I think I can do it. So that's why I am giving this talk. And I want to say this first theorem. So if B is a bounding cochain defined over F over some number field, and if you take this Galois group of F over Q, then we can twist this element by this Galois group. We have another element on the order dimensional cohomology. And we say that this is a solution. This is also a bounding cochain. It means that we have these equations that called the Molar-Cartan equations. Then the Molar-Cartan solution of the Molar-Cartan equations is somehow preserved by this Galois group actions. That's I think I mentioned some similar statement in the case of algebraic geometry. You have algebraic variety over Q. You have some sheaf defined over F. Then you can conjugate this sheaf by the Galois group action. So this is that analogy. And the next one is also analogy. So you have these two bounding cochain defined over F, and you take this Fourier homology using this twist. And this Fourier homology is originally defined over is a vector space over F. Well, actually, sometimes we need Novikov ring, but F vector space over F. But then if we twist this bounding cochain by this Galois group actions, so you have this Fourier homology of B1 sigma and B2 sigma. Then you have this sigma star. It's an isomorphism between Fourier homology. And this isomorphism is Q linear, and it's also twisted F linear. So twisted F linear just means that this formula, right? I just wrote before. Sigma star X is a sigma star X. So it's not F linear, but using Galois group. And this happens in the case of sheaf cohomology. So we have this kind of things. And then, so before going further, I want to explain a bit about cyclic cohomology. So the main claim is that everything is defined over Q in this sense. But to do to do something is symmetric, we need to kind of keep some symmetry. And the important symmetry is called the cyclic symmetry, because this is something related to Calabi-Yau structure. So let me explain what it is. So let me take, I think this should be X, I'm sorry. So we have some X n-dimensional manifold. Then you have this Poincare duality in a chain level. You have this P form and the Q n minus P form. They can just take wedge and integrate over X. So this is a pairing of and this induces pairing to the cohomology of Poincare duality on a cohomology. But this one has this symmetry. So you have MK, it's kind of operator called infinity operator. And you input the K differential form and you apply MK and take this duality with X0. So you have this complex number. Then you cyclically rotate this K plus 1 numbers. So MK, X0, XK minus Y, XK. And these two coincide up to some sign coming from the changes. And in this case, use your drum theory. This is quite obvious. So in this case, we have only M1 and M2. M1 is just a drum differential, and M2 is a wedge product. And in the case of drum differential and wedge product, this is a very easy thing to prove. I mean, in M1 case, this is, I think, a consequence of Stokes' theorem. And M2 is just the associativity and commutativity of the wedge product. So, but what we can do is that this cyclic symmetry, we can generalize to this including this holomorphic disk instanton effect. So our infinity category is cyclically symmetric. It's just this equality. And I explained that this property is actually related to this Calabi-Yau. So this is a chain level equality, and there is a homology version of this equality that is called the Calabi-Yau property. And why it's Calabi-Yau is something I want to explain. So there is something called a cell duality. So you consider complex manifolds defined over C. What is cell duality? So you have two sheaf, E and F. You take this home, and you take this cohomology. Then it's dual. You just you change the role of F and E, and you take N minus K cohomology. But you have to add this tensor of holomorphic N forms. So this is the famous cell duality. And so this looks very similar to Poincare duality I explained before. And this and also this Yoneda product of this sheaf cohomology is cyclically symmetric. But what's different is this presence of this omega n, because integrations of this d-bar cohomology, you have to kind of 0n form, so you have to wedge n0 form to have a well-defined integrals. But if you assume your manifold X is Calabi-Yau, it means that this omega n is a trivial bundle. So this cell duality just holds without any this collection of the canonical bundles. So this is why this cyclic symmetry is called Calabi-Yau property. And basically this Poincare duality in our Lagrange-Freya theory and also the cyclic symmetry corresponds somehow this trivialization of the n-form bundles. So it's something like a holomorphic n-form, and it plays somehow important role in the mirror symmetry. So I just explained after this Calabi-Yau property. Then I want to write a theorem. So we consider this. So first theorem is that boundary co-change. Then this Freya homology over F is defined, and then it is satisfied this Galois symmetry. And moreover, all the structures, like all the higher product and all this structures on this category is defined over F linear, and the Galois group acts in this twisted linear way. And among the structures, this cyclic symmetry and Poincare duality is also included. So we can construct a full structure which is cyclically symmetric and is kind of all the associativity relations, and everything is Q linear and F linear and F twisted linear. So everything is very works on this on a kind of over Q. And this is very similar to what we do in a sheaf cohomology. For example, if you have a projective algebraic variety defined over Q, and suppose that projective algebraic variety is a Calabi-Yau, it means the holomorphic n-form bundle is trivial as a Q vector bundles. Then you can prove this using this sheaf theoretical part. Okay. So now, okay, let us consider this one. So we can consider Hoshide homology over Q using this kind of things. Because in the same sense that Hoshide chain complex is acted So Hochschild chain complex originally is a F vector space, and the vector space over this number field. But this Galois group acts in the twisted linear way. So you can just take the fixed point of this Galois group. That's a Q Galois group. And the claim is that, so we have just some map from this Q Hochschild homology to Q homology over X. And the claim is that this is Q linear, and this is Q linear, and this Q structure here is just usual Q structure of this ordinal cohomology. And the open closed map is, I don't want to explain in detail, but this is something like this. You have this you have this disk with k plus 1 point, and you have this some output in the middle of the disk, and you have this k plus 1 thing in this Hochschild homology, and the output is something on ambient space. So you count this kind of disks to define this open closed map. So the theorem is just we can define this all structures over Q, so that it is so that even this open closed map is defined over Q. So as you see that this is something like a symplectic side of the story. In the complex side of the story, you have this kind of derived categorical coherence sheaf. Its Hochschild homology became this Hodge homology, which is the Q vector spaces, and you have a Q structure. And you, for example, you take the same algebraic variety as the symplectic manifold. You start from this category of Lagrangian submanifold. You take its Hochschild homology. You have this map to the ambient cohomology with transcendental Q structure. They are equal. So somehow the difference of these two Q structure is somehow related to this. You have two different structures. One is symplectic structure coming from Lagrangians, and the other is a sheaf theory, which so the sheaf theory gives algebraic Q structure, and symplectic and this Lagrangian Freya theory gives this transcendental Q structures, and some main player of this Hodge theory, it's a period integral, is in a sense a kind of pairing between the symplectic type things and complex type things. And in some cases, like singularity theory, this is very much visible. In a singularity theory, so you have some polynomial, Laurent polynomial or something defined over Q. Then there is something called the Jacobian ring, which is a ring over a rational number. And Q, algebraic Q structure is just the usual. So you take this Jacobian ring. For example, you take this W, so this polynomial. Then you take this differential of the W. So this is a ring, and this is defined over Q, and so this is the Q algebraic structures. And what is the transcendental structures in these cases? And there is some theory by Saito theory of primitive form. This one is related to some degree 2. I mean, this is the n dimension, so half-dimensional differential forms on ambient spaces. And there is a cycle, Lagrangian cycle, that's called the vanishing cycle of this singularity. And you integrate this, something corresponding to this by this vanishing cycle. That's a basic thing in a period, serial period. And the vanishing cycle is just a Lagrangian submanifold. In this case, open closed map is very much trivial. Yeah, just this this generator of this Lagrangian cycle to this homology class itself. In the case of P2, it's different because kind of this Lagrangian tora is homologous to 0. So reading all the term is trivial. So it's a bit non-trivial. But this duality can be seen that something came from Lagrangian, something came from sheaves. And that's generalized to rather much bigger classes. And let me consider the case of this, the case we studied, this CP2 1-point blow up. And this corresponds to 4 elements. And you have F, and the Galois acts transitively. And you calculate this Hochschild homology. It is actually this F tensor F itself. It's easy to calculate. And you take this Q part is just F. So this field F is a Hochschild homology. And P is an isomorphism, and this cohomology is actually the quantum cohomology of this X. You just put this Q is, I mean, T is 1. It's just this field itself. So there's this field. So this is a special case, and there are many other cases. I mean, in complete generality, it is expected that this P is isomorphism in a great generality. My conjecture is that it is isomorphism in a case when X is a algebraic variety. But so in many cases you have this. You can see this transcendental Q structures from this Hossid homology of the Lagrangians. So that's the story. So I just want to two slides about the proof. And the proof is kind of very much different from what I'm telling. So we in 2009 know that everything works over Q except cyclic symmetry. So if you look at a book in 2009, we use singular homology to build everything. It's a singular homology, so it is defined over Q. But if you look this book published in international press, we explicitly write, if you just look at geometric intuitions, it is very clear that this is cyclically symmetric and blah, blah, blah. However, we could not prove cyclic symmetry. One reason is that, so you see this Poincare duality, and the Poincare duality of a singular chain complex is highly non-trivial because intersection pairing with transversality is an issue. It's related to the following things. If you consider some chain model of the cohomology, you have some continuous map or smooth map, you may push out the chain or you may pull back the chain. Singular homology, it is very easy to push out the chain, you can just compose it. But pull back the chain in singular homology is very difficult. You have to kind of make this chain transversal to the map. Then you can take fiber product and then triangulate. This is a very complicated process. So pull back and push out is is very different. And if you look this formula of cyclic symmetry, you have to kind of handle pull back and push out in a very symmetric ways. And that's extremely difficult in singular homology. That's why we couldn't do it. And then what we do in more recently is that we change to drum theory. In the drum theory, pull back of the differential form is very easy. Push out of the differential form is a bit more difficult because push out of smooth form is distributions. But except this smoothness, so the stage is much better. So we carefully take care of this regularity theory so that we can make it work over real numbers. That's what we did recently. But then the issue is that since we use drum theory, we lose Q structure. Drum homology is not defined over Q. So what we do recently, what I'm doing is that, so now the solution is how to do this over Q is just, the construction is actually two-step. One, we construct something on a chain level. Then we use some homological algebra to get something on a homology. And the first step is geometric, and the second step is algebraic. But then we throw out algebraic step. We combine these two steps together with just one geometric step and try to construct this story directly on a homology group. So that's a way. But actually, there are a lot of technicalities, and I just begin to write it. So it is just yet in the beginning. Okay, thank you very much. I stop here.
Are there any questions? Yeah, I have one that in the example you have 4 flat connections, right? So in the toric case, do you have a description or estimate, like how many?
So the total number of the pair of Lagrangian plus flat connection is exactly Betch number. If everything is non-trivial.
Are there any other questions? If not, let's thank the professor again. All the morning speakers. So yeah, so that's all for the morning.
Yeah.
Thank you.
So welcome to the afternoon conference, and our first speaker is Professor Xiaoli Han, who will speak on some recent progress on the LYZ equation. Welcome.
Okay, thanks. So it's my great honor to be invited to call here. So first, I would like to thank the organizer for arranging this wonderful conference, which gave us a chance to gather together and share our ideas. So today, my talk is about LYZ equation. It is also the deformed Hermitian-Young-Mills metric. This equation has been introduced by Professor Fu Jixiang and Chen Gao. So maybe there's some overlap between my talk and their talks, but our focus are different. So, okay, so this is a joint work with Professor Jin, who works in Renmin University now. Let's start with some fundamental definition about the DHY metric. First, given a complex compact Cantor manifold X with a Kähler form omega, and L is a holomorphic line bundle over X. Given a Hermitian metric on this line bundle, then we can define the Chen curvature. Chen curvature F equal minus partial bar log H. If there's no square root of -1, then this Chen curvature is the imaginary 1-1 part. Well, it's well known the Kähler form is a real 1-1 form. So omega minus F is just complex. So then we can define a complex function on X in the following way. We take omega minus F to the N over omega N. Then this is a function, complex function on X. For this complex function, we can define the argument. We define it as theta in the sense of module 2 pi. And the goal is to look for special metric on this holomorphic line bundle. This special metric is called deformed Hermitian-Young-Mills metric. We simply call it DHYM metric. A Hermitian metric is called DHYM metric if the argument of C is constant. Now, what's C? So let's see. If we take the average of C on X, that means we integral this complex function on X, then we get a complex number. This is a complex number. This complex number only depends on Kähler class and the Chen class. It is independent of the representative of the class. So if we define the argument of this complex number as theta hat, then theta hat is a topological constant. So according to the definition of DHY metric, if this argument of C is a constant, then this constant should be theta hat. So the DHY metric is equivalent theta equals theta hat in the sense of module 2 pi. Okay. From the definition of DHY metric, we can get two equivalent definitions. The first one follows directly from the definition. Since the theta is an argument, so the imaginary part of this quantity equal tangent theta times the real part of this quantity. If theta equals theta hat, then this is a DHM metric. So it's easily follows from the definition. The second equivalent definition can be read as this elliptical equation. So how to deduce this elliptical equation? So let me explain. fix one point, we choose a normal coordinate such that the omega is identity and the real part of the curvature is a diagonal matrix. We suppose the angle value is lambda I. Now, then omega minus f to the n can be factored into the product of these n terms. So for each one term, the argument is arctangent lambda I. So the product of these n times is the sum of arctangent lambda I. So DHYM metric can be read as the sum of arctangent lambda I equals theta hat. If we take the derivative of arctangent about lambda, then the derivative is 1 over 1 plus lambda 2. This is a positive. So this equation is elliptic. So that's the second definition. So now compare this DHY metric with Hermitian-Young-Mills metric in case n equal 1. That means now, this is for the x. Now x is a real remaining surface. The real dimension is 2. Now the imaginary part of omega minus f just square root minus 1 times f. And the real part is omega. So DHY metric is equivalent. This imaginary part equal tangent theta hat times the real part omega. This equation just the Hermitian-Young-Mills metric on n equal 1. So in n equal 1, these two equations are exactly the same. For this reason, I think this equation or this metric is called the DHYM metric. Next, let's compare a DHYM metric with a special Lagrangian equation. A special Lagrangian equation has been introduced by Chen Gao. So let's recall here again. We're given a Calabi-Yau manifold with Kähler form omega and a holomorphic volume form big omega. An n-dimensional submanifold L is called Lagrangian if the restriction of the Kähler form to L is 0. Furthermore, if the imaginary part of E minus IC times big omega is 0, then it is called a special Lagrangian submanifold. Let's see the most important example of Lagrangian graph in Rn times Rn. We know the gradient of the graph of the gradient of one function is always Lagrangian submanifold in Rn times Rn. And a beautiful result of having Lawson tell us if it satisfies this equation, then this submanifold is special. So here the lambda I is the angle value of Hessian matrix of U. We can see the deformed Hermitian-Young-Mills metric are defined on complex manifold. So it is complex. But now the special Lagrangian submanifold, this equation is defined on Rn. So it is a real equation. But they have the same exactly form. So the DHY metric can be viewed as a complex version of a special Lagrangian equation. The motivation of studying DHY metric comes from the mirror symmetry in physics. It was first defined by these 4 physics in 1999. Roughly speaking, mirror symmetry just describe the correspondence between the holomorphic structure and the symbolic structure on Calabi-Yau manifold. And later, Liang, Yau, and Zaslow mathematically formulated this equation. So now we call this equation as LYZ equation. This equation is related to the geometry structure and the behavior of some physical quantity. So now it become more and more important. Okay, in our previous discussion, we need to use the geometry structure of a holomorphic line bundle. Now we can forget all geometrical information from the holomorphic line bundle. We just fix one real class in X. Now we also can define this complex number, use the Californ and the alpha. And this complex number is also dependent only on the Cal class and this fixed class. So if we want to define the argument of this complex number, we need to assume this number is not zero. So we need this condition, this such non-degenerate condition. If it is not zero, then this argument is well defined. So in this case, we see the omega and alpha, the pair of omega and alpha satisfy our equation if they satisfy this equation. Okay, so the equation is same as before. But in that case, the goal is to look for some special metric on holomorphic line bundle. Now, the goal is to look for special one-one form. So this equation is called the formal form version of our equation. So we know any representative of this class can be written as one fixed one-one form alpha plus some partial bar phi. So this equation can be translated into the equation about phi. So look for the special one-one form becomes to look for the special function phi. We suppose the angle value of alpha phi is lambda I, then the equation is the sum of arctangent lambda I equals theta hat. The equation is the same. Now we define the phase operator, big theta, as the sum of arctangent. Since the value of arctangent lies in minus pi over 2 to pi over 2, so the big theta omega is less than n times pi over 2. So according to the value of this phase, we can give two conditions. One is a supercritical phase. If this alpha, if theta hat is bigger than n minus 2 times pi over 2, then we say alpha has a supercritical phase. Another one is a hypercritical phase. If theta hat is bigger than n minus 1 times pi over 2, then we say alpha has a hypercritical phase. So hypercritical phase is stronger than supercritical phase because the sum of arctangent is greater than n minus 1 times pi over 2. So every arctangent must be positive. That means every angle value lambda I is positive. So in this case, this phase operator is convex. So we can use Evans-Koloff theorem to get a higher order estimate while solving this equation. In supercritical phase, this operator is not convex because maybe there are some negative angle value. But we can prove in supercritical case, there is at most one angle value, which is negative. So furthermore, we can prove the level set of this operator are convex. We still can use Evans-Koloff theorem to get a higher order estimate. So in the following, we always assume the class has a supercritical phase or hypercritical phase. In other cases, we cannot deal with now. Okay, this equation has been initiated to study by Jacob and Yao in 17. In the paper, they define one functional, which is related to the angle value of the curvature. They found LYZ equation is the Euler equation of this functional. So if in PDE, if one equation comes from the Euler equation of one functional, means this equation is good. So this LYZ equation has a good variational structure. So now we want to solve this equation. So the first result is on the Kähler surface. This result is in the paper of Zhao Ya. They found in this case, that means n equal 2. In this case, LYZ equation is equivalent to the Monge-Ampere equation. And according to your solution to the Calabi conjecture, this equation exists a solution and is equivalent. The left-hand term is positive. So they give a necessary and sufficient condition for the existence of our LYZ equation. It is equivalent. This class is positive. This is a 1-1 form. So in general, for high dimension, there exists abstractions to the LYZ equation. Collins, Xie, and Yao in 18, they give a necessary condition. If there exists a solution to LYZ equation, then this complex number should not be 0. So we need more condition in order to solve this equation. And in the same paper, and Jacob and Yao give another condition. The condition is the curvature. They assume the manifold has a non-negative orthogonal bisectional curvature, and the class has a hypercritical phase. This condition is strong, hypercritical phase. Then it means a smooth solution to this LYZ equation. So we try to remove the assumption on the curvature, but it is non-trivial and it's difficult. I think we need require more ideas. So in another paper, Collins and Jacob Yao gave an analytic condition. They in 2020. In that paper, they assume this class has a supercritical phase. This condition, they can relax this condition. In this theorem, they assume hypercritical. So that means every angle value is positive. Now they can suppose this class has supercritical phase. That means there may be one negative angle value. And if in this class there is a representative T for each j, the sum of arctangent mu I, where the index I is different from j, is bigger than theta hat minus pi over 2. Moreover, they assume the phase is bigger than n minus 2 times pi over 2. Then there exists a solution to this equation. This condition, the third condition, is equivalent to the C subsolution for following nonlinear equation. And this kind of definition, C subsolution, is first proposed by Guanbo in 14. But this is for real equation. And Sakhelidi gave an equivalent version for complex equation later. So here, this equation, this condition is a C solution, some kind of a C subsolution. In that paper, in Guanbo's paper, Sakhelidi paper, they only assume if there exists a C subsolution, then there is a solution to the equation, to that equation. So in their paper, they need another condition, the for condition. So we think this condition is superfluous. Then Collins, Jabor, Yao conject maybe there existence theorem is true without the condition for. So this conjecture has been verified in several cases. The first case is n equals 3. Pincali can solve this equation without the condition for. And for n equals 4, Chaoming Lin confirmed that their conjecture without the condition for. Later, he claimed he can solve this equation without the condition for all n. But until now, his paper hadn't been published yet. So, this is I called this analytic condition, and this condition, this equation can be solved. Another condition I called algebra geometry condition. So, as an analog of Nakai-Matsu type criteria for a Keller class by Damai and Paul. So there is also a Nakai-Matsu type criteria for the LYZ equation. I see it here. Now we fix one class. This class always has supercritical phase. Use this class and the Keller form, we can define PP form. This is a PP form using the real part and the imaginary part. And Collins and Jiahua Yao conject if there exists a solution to LYZ equation, if and only if the integral of this PP form on any subvariety of dimension P is positive. So if this integral is positive, then there exists a solution. So the first, we can check this conjecture n for n equal 2. Now this is a Keller surface. Now P only can be chosen as 1. So the 1-1 form is alpha plus cotangent theta hat omega. This condition, so this integral is equivalent to this 1-1 form. The integral of this 1-1 form on any curve is positive. So it is equivalent to this class is Keller. So this result is proved by Jacob Yao. So in this case is right, this conjecture is right. And the first big breakthrough is made by Chen Gao in 21. He cannot prove the conjecture, but he can prove if along some text family, there exists epsilon is bigger than 0. For any subvariety, the integral is bigger than epsilon times some constant. Then it is equivalent to the existence of a solution. Later, Chu, Lei, and Tasky give another equivalent condition. In the theorem, there are 2 conditions. For condition is the integral on x. They claim if there exists one calorimetric T such that this PP form, which this n minus p wedge form, the integral is greater than 0. And for any subvariety V, the integral of this, for any m-dimensional subvariety, and this MM form is greater than 0, then there exists a solution. Here, they always assume that this class has a supercritical phase. So, and these 2 conditions, they can prove there exists a solution to LYZ equation. So using this theorem, they can prove if X is projective, then this conjecture is true. But in general, this conjecture is not true. And John construct the counterexample in general case. So this is a geometry. I think this is the algebra geometry condition for the existence of the solution. The last one? Yeah, subvariant P. But the M is less than N. Yeah, we need to check all these the MM form on all subvariety of dimension M. M is less than N. Okay, so in the following, in the previous discussion, we discussed the existence of weather equation. Now next topic is chain number inequality. The chain number inequality play very important role in the study of canonical matrix. For example, during the proof of Calabi conjecture, you prove the chain number inequality for canonical matrix. So here for our weather equation, Collins and Yao also can prove the following chain number inequality for dimension 3. And they assume this the phase is in a hypercritical case, then they can prove the following chain number inequality holds. A beautiful result is due to Chu and Li, then can prove the converse of the theorem is true. Namely, if the chain number inequality holds on three-dimensional manifold, then this weather equation can be solved. So I just state the theorem roughly. So actually, that's another condition which guarantee the theta hat is well defined. And Collins and Yao conject the chain number inequality still holds on four-dimensional manifold. But they conject it's only true for hypercriticals. And Jin and I can prove this conjecture on supercriticals. We can prove if theta hat is supercritical case, then chain number inequality is still hold. And inspired by the work of Chu, and we still want to prove if the chain number inequality holds, then the equation can be solved. So recently we can prove this theorem, but we need two conditions. The one condition is chain number inequality for four-dimensional manifolds hold. But another condition is for three-dimensional subvariety, the chain number inequality for three-manifolds still holds. And sure, there are other conditions which guarantee the phase theta hat well defined. And these are two conditions. But now it's in a hypercritical case. So that means lambda I is positive. And these two conditions we can solve this equation. The idea of the proof is to check these two conditions holds, and that two chain number inequality. Okay. So maybe next topic is about parabolic flow. So we want to solve this equation. We also can use the parabolic flow. So this now, because now this holomorphic line bundle, so the difference of H2 metric just can be can be measured by one function. So we this flow is introduced by Jacob and Yao. So that we define this parabolic flow. We suppose the function u evolve according to theta minus theta hat. And now the flow is called line bundle miniature flow. Why it is called line bundle miniature flow? Because in Lagrangian submanifold in Calabi-Yau manifold, the gradient of theta is just the mean curvature. So I think in this sense is called line bundle mean curvature flow. We want to use this flow to find the DHY metric because DHY metric is a stable point of this flow. And in that paper, first they prove if the gradient of the curvature is uniform bounded, then all derivatives are bounded. So here T is a maximum existence time. So if T is finite, then the flow can be extended beyond the T. And if T equal infinity, then the flow converges to a smooth DHM metric. So compare with the miniature flow, the gradient of the curvature behaves like the second final form of a submanifold. So in miniature flow case, if the second final form is bounded, then flow can be extended. In this case, if the gradient of the curvature is bounded, then the flow can be extended. And about this flow, Jing and I studied the stability of this flow. That means if we assume the initial metric is close to a DHYM metric, then the flow exists for a long time and converges to a constant. Thus, is close to a close means the second derivative of U0 is small. We can prove the smallness property can be preserved by this flow. So another result is epsilon regularity theorem for line bundle miniature flow. This work is inspired by epsilon regularity for miniature flow. This is proved by Brown-White in 25. He defined one density, which is related to the heat kernel. And he can prove that if this density is not less than 1 plus epsilon, then the flow is regular. This is a local result. They just consider the flow on some neighborhood. So then if the density is small, then the flow is regular. So we also can consider this kind of epsilon regular theorem for line bundle miniature flow. This is a joint work with Yamamoto. He was a student of Professor Futaki. Now he worked in Japan. We need two conditions. Roughly speaking, the first condition is called semi-flat. That means we can split this manifold into the product of two balls, and the metric only depend on is not trivial on only on one ball. Another ball, the metric is flat. Another condition is called graphic. That means there exists, we assume there exists a non-vanishing holomorphic section. And this the metric act on this section, the derivative is 0. And these two conditions, we can prove the similar epsilon regular theorem. Because the density here, our density is very complicated, so I didn't write it exactly. Roughly speaking, our theorem is if we assume the curvature is bounded and the density is less than 1 plus epsilon, then we also can see this flow is regular. So this is our work. There are other parabolic flow. For example, Takase introduced the tangent Lagrangian flow. That means they revise the right hand as tangent theta minus theta hat. And Fujixiang, Yao, and Zhang, they also consider the cotangent Lagrangian phase flow. They revised the right term as cotangent theta minus cotangent theta hat. Because Fujixiang has detailed this flow, so I think I will stop here. Okay, so thank you.
And we still have a few minutes for questions.
Yeah, thanks for the talk. So for your epsilon regularity result, the density you use, does it satisfy the any monotone property analogous to the Huisken spontaneity formula from incorrigible?
We hope so. Actually, we want to prove, but until now we cannot prove because the density is very complicated.
Okay.
It is related to the second derivative of the curvature.
Okay. Is it a Gaussian term or just?
Yeah.
Okay. And I guess you also mentioned some flow introduced by Jixiang Fu and Professor Yao. Are those flows also variational? They are gradient flow of some functional?
So you can see for that flow, the stable point still be DH1 metric, but but I just can see the behavior of the flow is different.
Sorry, when you say stable point, do you mean if you stable in the perturbation sense?
No. Or if you have a convergence, then they converge to the DH1 metric.
Okay.
So the right term is 0. That means the cotangent theta equal tangent theta hat.
Okay.
Okay.
So the static solutions are the
yeah. So all these flow, the static solution are all DHM.
Okay. I see. Yeah.
Thank you. And any more questions?
So how about it's a number inequality? So it's only so far it's only for surface and it's 4 it's 3-fold.
Yeah, yeah.
So you said the idea is to check the condition the bunch of inequality in the three.
Two.
So
No. Chen number inequality.
So you said the idea is to check. So go back to that slide.
Yeah, the idea is come from this dimension.
So you said that to check the
this one.
To check.
No, the Chen number inequality implies the solution of LYZ equation.
So what's the idea?
The idea is used to check this two quantities.
So the question is, this is for higher dimensional case, for general dimensional case. Why is it only for? So why the result is only stopped for 4-dimensional?
Oh, because for high dimension, the Chen number inequality is difficult to formulate. For you can see for 3-dimension, the Chen number inequality just one inequality.
Yeah.
But for 4-dimension, there are 2 inequality. So I guess for 5-dimension or high dimension, there are more inequality.
More inequality.
Yeah.
So it looks like it's more combinatorial because you have some cone. I mean, this how to say? So there is have a bunch of inequalities, right?
Yes,
It
yes.
appears. And here, but it's strange. But here you have a no control on the subvariety. So it's all about X. But there you have all about V. You have a subvariety V. How could you get that? So it's sounds very strange.
So if you assume the RYZ equation have a solution, then on subvariety, this similar equality is also hold.
Yeah, but you said that you have, so you want to check the once this inequality holds, then you have a solution. So for me, it sounds like this equality only for the high the third power of C1. You want to show that use all the go the upward. So go back to that slide. You have look, you have so many about V. About V, you see you have this integration around the V, but you have no idea about V. It looks like.
No, if you assume the number inequality for top dimension is right, then for high dimension is also right. It's easily can be checked. So for this part is easy.
This part is easy.
Yeah. So this is difficult to check.
Oh. Okay.
So and their condition. Actually, at their condition, this condition and the number equality, they can check the class of alpha is a color. So they use this as a test function here.
Oh yeah, yeah. Oh, I see. Okay. Okay. Oh, alpha. You assume that the alpha is killer.
Yeah.
Okay. But you said that for high dimensionals, maybe you have several inequalities.
Yeah. Yeah.
This is a conjecture. So it's a surprise to me. I mean, nobody conject this, but suddenly you have the converse directions. So it's really, for me, it's not so clear.
Yeah. So this result, I think, is very beautiful.
Yeah, it's beautiful.
Yes.
Thank you.
Thank you. And we have to move on. So where is our next speaker? Oh.
Okay, thank you.
Thank you. All right, so it's my great pleasure to welcome Professor Sebastian Picard, who will give us a talk titled Special Lagrangian Submanifolds and Circle Collapse on K-suite surfaces. Welcome.
Okay, yeah, so thanks to the organizers for the invitation. It's my first time in China. It's been a great experience so far. So this conference is, one of the themes is celebrating the 50 years of the Calabi conjecture. And so our story will also begin there. So we'll be working on a compact Kähler manifold. We'll be using little omega for the notation for the Kähler form. And we'll be working on the Calabi-Yau setting. So we'll also have a holomorphic volume form. We'll be denoting that holomorphic volume form by capital omega. So Yau's theorem is about finding an optimal representative in a given cohomology class. So you're given a cohomology class, and you want to find the best representative in there. And in this case, the notion of best representative comes from solving a nonlinear PD or geometric equation. So Yau's theorem is about finding a Kähler-Ritchie flat metric inside a given cohomology class, or you're given any Kähler class, and then there exists a unique Kähler-Ritchie flat metric in there. So that was 50 years ago, right? So what's next, right? And so many of us at this conference, we've all been working on various aspects of that question, right? What's next? What comes after Yao's theorem? And we've heard all about many different directions and so on. For this talk, what's next? We're going to be talking about special submanifolds. So here's the direction that that we're going to be heading towards. So you have a compact Ritchie-flat space, or a compact manifold with a Ritchie-flat metric G. And then you want to find special submanifolds in this space. And so we'll take the same kind of philosophy of looking for a special representative in a class. So for this problem, what's the class? Class is homology class. So if you're given a submanifold in your compact space, and then you take the homology class, you want to find if there's a special representative in there. And so what's the notion of special representative for this particular problem? We're going to look for representatives which minimize the volume. So we want minimal surfaces, but in particular ones which are volume minimizing inside a given class. And those will be, we'll just call these special submanifolds, which are ones which minimize the volume inside a given homology class. So that's the general problem that we'll be exploring. And that's the wrong direction. Okay, so for Calabi-Yau, there are two distinguished kinds of special manifolds. Basically, they come from the two natural calibrations, right? So in Mutao Wang's talks this morning, we heard about calibrations. And so on a Calabi-Yau threefold, what are the natural calibrations that come from the geometry? So you have the two forms, you have a little omega and a big omega. So using little omega and big omega, you can use these as calibrations, and you can look for calibrated submanifolds, and these will be volume minimizers in a homology class. And so we'll call these our special submanifolds. So let's start with little omega. So you take little omega, you want to use that as calibration. So little omega is the Kähler form. So you can also just raise it to powers. You don't just need to take little omega, you can take little omega to the power of k. And all those are closed comass 1, so you can use these as calibrations. And Wertinger's inequality says that if you have calibrated submanifolds with respect to these little omega, then in fact it's a holomorphic object. It's a holomorphic submanifold. So this is a way for differential geometers to attack these problems of constructing holomorphic submanifolds. So of course there's techniques from algebraic geometry to construct holomorphic objects, right? Or complex analysis, you can use theory of holomorphic functions and so on to construct holomorphic objects. But here's an equation that allows us to use like smooth manifold geometric analysis. This is a conference on geometric analysis. We want to use implicit function theorem or smooth techniques. And we can do it via this equation, this calibration equation. So using this calibration equation as just like a smooth PDE, we can attack it using geometric analysis, construction special cycles, and then by Wertinger's inequality, that's what tells us that actually we find such a submanifold and it's locally carved out by the zeros of holomorphic functions. But we can get at it indirectly by geometric analysis without having to use, or without necessarily using complex analysis. So that's one of the insight of Wertinger's inequality, and that's what we'll be doing later on. We'll be constructing holomorphic curves by means of geometric analysis, and the way we'll construct them is by using this equation here, this calibration condition for little omega, and using implicit function theorem and so on. So there's a second type of special submanifold in this context, right? So Calabi-Yau, we have our two forms. We have our little omega, our big omega. We use both of these as calibrations. We get our special submanifolds. So what about big omega? So if you use big omega as your calibration, well, this leads you to the special Lagrangian equation. So these are the submanifolds of half the dimension. They satisfy this equation here, where the real part of capital omega restricts to the volume. And if you solve that equation, then you have again a minimizer of the volume in a homology class. So this equation was introduced by Harvey Lawson. But perhaps as another theme of this conference is how equations from string theory and supersymmetry somehow point out fundamental equations from geometry, right? So we have two of the themes of the conference: the Calabi conjecture, Taylor-Ritchie flat metrics, Uhlenbeck-Yau theorem, that's Hermitian-Yang-Mills. So both those equations were also independently rederived in string theory, right? So Candelas, Horowitz, Strominger, Witten, they found the Taylor-Ritchie flat equation, right, from looking at constraints from supersymmetry, supersymmetric equations led them to Taylor-Ritchie flat equation. And actually, basically in that paper, it also kind of directly leads to the Hermitian-Yang-Mills equation. That's if you put a gauge bundle into the theory, you're also led to this Hermitian-Yang-Mills equation. But continuing along this theme with this principle of string theory and, well, specifically supersymmetry, physicists have been re-arriving in many different contexts these special geometric objects. And here's another one. So Becker-Strominger independently re-derived this equation of special Lagrangian. Real part capital omega is devolved by just reasoning in supersymmetry. And then I guess I was told it was Yau who then pointed out to them after. So that paper doesn't acknowledge Harvey Lawson. They weren't aware of it, right? And it was Yau himself who told them this equation had already been found, right, by Harvey Lawson before. But they arrived there from a completely different direction than Harvey Lawson. They're just using equations from supersymmetry. I guess the last digression before moving on is that so this equation for special Lagrangian, it's really not an equation about little omega or the symplectic structure. It's really purely an equation. It's not it's not necessarily about symplectic geometry, though the name is special Lagrangian. Really, the equation only involves capital omega. So it's really an object which only has to do with the complex structure, complex analytic structure of the complex manifold. And this is, in fact, pointed out if you look at Harvey Lawson's original paper. So they proposed to study this equation on complex manifolds with trivial canonical bundle. So you only need the capital omega, which may or may not be Kähler. So they say Kähler, it could be Kähler or not, right? That's not the fundamental thing. It's really, it has to be Calabi-Yau in the sense of having a calibrating form, right? As having this holomorphic volume form, and you use that after perhaps conformally rescaling your metric. So if you're non-Kähler, you can do conformal changes of your metric to ensure that the pointwise norm of this is 1. That's easy, that's trivial. If you have Yau's theorem, then you can ensure that it's Kähler and with constant norm, right? And so in a sense, the theory is richer when you have a Kähler-Ritchie flat metric, but it's not necessarily, Harvey Lawson kind of proposed this equation for these special submanifolds just on a complex manifold with holomorphic volume form. Right. Okay, so those are two main classes of special submanifolds on a Calabi-Yau. Right. So okay, so we want to do geometric. We're geometric analysts. We want to construct special submanifolds, right? We want to construct. Oops. That was the previous slide. Oh yeah, okay. So before, let's drop in some famous problems. All right. So the theme so far has been finding special representatives in a given homology class. So here are two very famous problems, not precisely stated. We're just going for the big philosophy here, which is that if you have a submanifold, you take the homology class. When can you find a special or optimal representative in that class, right? Just like Yau's theorem, as you have a cohomology class, you can find a special representative Kähler-Ritchie flat in that class. Here's two famous problems about if you're given a class of a submanifold, can you find a special representative in there? And in this case, it's these calibrated cycles in one context holomorphic, or in the other context, special Lagrangian. But as emphasized by Yao throughout the years, that these should more or less have equal importance because they're really just about finding these special cycles inside a given homology class in this case. Okay, so we want to do geometric analysis, and we want to construct these special submanifolds by means of analysis. And so our setting is a compact Ricci-flat ambient manifold. And so how do we construct special submanifolds? The main problem being, of course, we don't have explicit formulas for the Taylor-Ricci-flat metric. So if we're just in the bulk region of the moduli space, we just have Calabi-Yau metric, a Calabi-Yau manifold with a metric. How are you going to start? How are you going to, what do you have to work with, right? And so the idea, I suppose, is an idea that comes in many different branches of mathematics, is that once you have a parameter or you have things that comes in families, you can tune those parameters to either crank them out to infinity or turn them off to 0 and hope to see something a little bit simplified in the limit and try to work back from there. So Calabi-Yau metrics often come in families, right? So we have Kähler moduli, vary the Kähler class. You have complex moduli. You can vary the complex structure. And so you have these parameters floating around in your given situation. And then you can start tuning those parameters and take them to extreme limits and see if then you'll gain a better understanding of what's happening, of what's going on. So so that's the direction we're going to take. So we'll be looking at a particular example, but we'll be kind of tuning these parameters to an extreme limit. We'll see something a bit more simplified, and then we'll try to reconstruct submanifolds nearby that extreme limit. So if you have the moduli of all Calabi-Yau structures, maybe in the bulk, we're not so clear what's going on, but then in certain corners, near certain limits, maybe we have a better understanding of what we're doing. So that's theme. So this is more general philosophy. It's not a precisely state. This is going to be more of just a theme of our talk rather than a precise conjecture. And it's inspired by the SYZ conjecture, although this is not the precise SYZ conjecture about T2 fibrations and so on. This is more just generally inspired by the SYZ. Kind of zooming out in a more general setting, the theme is simply taking degenerations of compact Ricci-flat spaces and getting an affine object in the limit. And it appears that in many contexts, there appears to be a correspondence between graphs and certain combinatorial data on the affine limit. So the affine limit is much simpler, right, than the compact Calabi-Yau. And so you can write these simpler objects such as graphs, maybe with some combinatorial data on the affine space. And it appears in many situations there seems to be a correspondence between those simpler objects and the more complicated objects of calibrated cycles or special submanifolds of the compact Ricci-flat space near that affine limit. So we'll be talking about Calabi-Yau threefolds, but this phenomenon can also be observed at G2 settings and other settings as well. But that's the kind of big general theme of what we'll be discussing. And as differential geometer, we can consider the following lifting problem. So say you have these structures X epsilon, right? So that's a sequence of Ricci-flat, compact Ricci-flat spaces, the Calabi-Yau spaces. And let's say they're collapsing and degenerating. So you have this parameter, you tune the parameter, the whole thing collapses down. You've got an affine base of lower dimension, whatever that is. And then depending on your context, you'll have a suitable notion of graph and combinatorial data on this base B. We'll see examples in a moment, which is generally speaking, some linear thing, some edges with vertices, perhaps some weights on the vertices on the base. And the lifting problem is you want to reconstruct the submanifolds along the sequence. So you want to go back from the base, the affine base, up to the sequence of special submanifolds on the compact Ricci flat space. And so the whole ambient space, X epsilon, that's degenerating to the lower dimensional base. And then you want the special submanifolds, sigma, those to converge, to collapse down to the lower dimensional object, the graph, collapse down to just a graph on the base. So that's more or less the general philosophy for what the kind of examples we'll be looking at. Okay, so first, so here's there's nothing deep happening here. For this is just a very trivial example, but at least it's an example of this phenomenon that we're describing earlier, which is just you'll have some affine base, some graph. In this case, it's a stupid graph. It's a single edge, nothing more. That's it. And then from that, we'll just lift it to a bunch of special Lagrangians. So let's just take T3 as our affine space. Just take just a straight line embedded one, just a single edge, if you want to think of it as a graph, nothing else. And well, there's nothing deep going on here. You can just put a collapsing circle on top of that, right? So from the affine three-dimensional base T3, you get a Calabi-Yau twofold T4. And so all that's happening is the circle is collapsing as epsilon goes to 0. So the affine base is just, you add an extra circle, you get a T4. And the graph on the base, which is just a straight line, well, you just put the circle on top of that, you get a T2, which is collapsing. So as the circles collapse, the T2 just collapses to a straight line. And those T2 are these special Lagrangians, special submanifolds in the ambient Calabi-Yau. So that's just a very basic illustration of this broad philosophy that we were mentioning before. Okay, so the project that we set off to, we set off to try to find an analog of that basic example for K3. So we're looking at Calabi-Yau twofolds. Well, it's either T4 or K3. So T4, you have that phenomenon that I just showed there. So we just asked, what's the analog for K3? We just want K3s where a circle collapses, get an affine base, and then look at some simple lines with perhaps vertices on the base and try to lift them to special Lagrangians in the ambient Calabi-Yau twofold. I guess I should say at this point, right, so at the beginning of the talk, we talked about the calibrations and the little omega, big omega, special Lagrangian holomorphic curve. In this setting, we're just talking about Calabi-Yau twofolds, hyperkähler. So up to hyperkähler rotation, you can go from one to the other. So I'll just be saying special Lagrangian, but everything I say also applies to a holomorphic curve after hyperkähler rotation. So it's just a choice of nomenclature. I'll just be saying special Lagrangian, but it's the same statement for holomorphic curves. In this case, it doesn't matter. You have hyperkähler rotation. Okay, so we're looking for the analog of this basic thing. What's the K3 version of that? So Sun Zhang have a classification of degenerations of hyperkähler structures with normalized diameter, and there's the list. And they are all affine, right? So this is back to this theme that these degenerations of Calabi-Yau should collapse down to affine limits, and in this case, it's totally classified. You can have an affine base of dimension 1, 2, 3, and here they are. It can collapse down to just an interval. So the four-dimensional four-manifold, the K3 just goes down to a 1D space. Case 2 is the traditional SYZ setup as done by Gross-Wilson, where in case 2, you have T2s, two torides, half the dimension, whereas you have the four-dimensional four-manifold, you have the T2s half the dimension, the T2 fibration, the special Lagrangian fibration collapsing, you have your base of dimension 2. But case 3, that's the one that's the closest analog to our example from earlier, which is just a circle collapsing, where you have four-dimensional going down to 3. So basically, you know, the SYZ setup is 2 + 2 = 4, right, in this case. But the case that we'll be talking about today is 1 plus 3 equals 4. So we have a one-dimensional fiber collapsing, and then the 3 for the affine base equals 4, the total ambient space. So that's what we'll be exploring. And the construction of K3 in this case was done by Lorenzo Foscolo. So that was the construction of K3 surfaces collapsing down to a 3-dimensional affine limit. So basically, the construction goes as follows. You have the singular points on the affine base. Oh, right. So the affine bases, they're not smooth, right? They have singularities of T3 mod Z2. There's the fixed point. So there's going to, so it's not a manifold, but it's an affine space. And away from those special points, you just construct a principal bundle. And it's a literal S1 fibration, but it's non-compact. So you basically take away some points on the base. You construct this non-compact fibration where they have the S1 fibers. And the main problem is the compactification problem, is how do you compactify this fibration to a compact manifold. And so that's what Lorenzo Foscolo does in this case. By gluing in suitable local models and perturbing, he can compactify the space to a compact K3. So that the K3 itself, it's only an S1 fibration on a large open set. Those open sets get bigger and bigger and bigger and eventually fill out the whole thing. But at any fixed moment in time, it's not literally a fibration. There's a small piece of the manifold where it's just been glued in another local model. But on the bulk of the space, it is just a S1 fibration, and that region where you have the fibration just gets bigger and bigger and bigger. There's a volume of the proportion where it is a fibration eventually goes to 1 and fills out the entire thing. Okay, so that's the Calabi-Yaus degenerating to the base. And so we want to talk about special submanifolds. So we want to construct special submanifolds by lifting graphs on the base B. And that's, so here's our theorem. So this is joint work with Federico Trinca. And so the class of graphs that we're lifting is the following. It's an edge with 2 vertices. So it's very simple. This is just kind of a toy model to play around with these ideas from the big, these big broad programs from early on. We just want some specific examples where we can really just get working. So this is very simple. It's just on the base, it's just one edge, 2 vertices. And then you got to put some weights on the vertices. The weight condition in this case is they just sum to 16. That has to do with the fact that you want to reconstruct a K3. It's got to close up. So for the torus, you didn't need those stupid weights. You just take the edge, and then you would reconstruct T4. But if you want to reconstruct a K3, then there's an Euler characteristic condition, and then this is where this sort of balancing or weight K1 plus K2 condition comes in for the topology. And so we lift this graph plus combinatorial data to a special submanifold. So the edge corresponds to 2 spheres which are elongated. They're converging back to the line. So they're getting thinner, like thin tubes, thinner and thinner and thinner until they converge to this line. And the vertices, those are shrinking spheres. So there's going to be a bunch of shrinking round 2 spheres that are going to be getting crushed down to those points P1 and P2. And the number of spheres that are going to go down to those points, that comes from the K1, K2. The weights tell you how many spheres are going into the vertices. So the vertices of the graph represent a chain of shrinking spheres. And the edge corresponds to an elongated sphere. And so, yeah, and these are special submanifolds. So these are special Lagrangian or holomorphic, whatever you want to talk about depending on hyperkähler rotation. But anyways, they're volume minimizers in a homology class. So there are these, 2 spheres in a 4 manifold minimizing the volume in the homology class. It's going the wrong way, apologies. Let's draw a picture. So so let's once more recall the construction of the ambient space, right? So you have the K3 four-manifold degenerating down to a three-dimensional base. And the K3 on this large open set, it looks like a circle fibration, just a bunch of circles. And then you have these bubbles. So you have these bubble regions. Those are shrinking, getting smaller and smaller and smaller. And in the bubbles, you have these local models. So for this problem, the local model you have is these Taub-Nut local models. So those appear as bubbles in the K3. And as you tune your parameter, the bubbles shrink to the points. And on the fibration, on the bulk outside of those bubbles, the circles are shrinking. And so the first part of this theorem was essentially already known. It basically follows from work that was done before. So inside the bubble, you have the local model, the Taub-Nut local model. Everything's explicit. And you can draw those spheres, no problem. It just depends on the monopole points. Basically, you have two monopole points in the Taub-Nut. You just draw a line between them, and then you lift the circle. The circle action collapses at those monopole points, and so that gives you a sphere. And then those are holomorphic or special Lagrangian in the local model. That's going to receive global corrections from because we're not just in a local model, we're in a compact K3. And so, of course, the local model metric is corrected by the contributions coming from the compact. But those are small, and then you prove those are so small that you can perturb your minimal surface or special, whether you want to look at it as holomorphic curve or minimal surface, or use Maclean's theorem and special Lagrangian. If you have a submanifold which is approximately solving your special equation, and your ambient data is uniformly controlled, then you can perturb it a little bit and get a genuine solution. So that explains the chain of spheres inside the bubble that are getting crushed to points. So that was more or less already known. It follows from Fosco's construction more or less directly. So the main technical part of this work is the elongated sphere, which is spanning the two bubbles. So you have in the global K3, you've got a bunch of bubbles around there. You take two of them, and then you start from one bubble, and you traverse all the way through the bulk into the second bubble. And this is the object that we want to perturb a little bit to be special Lagrangian or special cycle, special submanifold. So we'll spend the rest of the talk just giving some ideas of the proof. So it's going to be a gluing construction. So it's just a gluing construction for this sphere, which connects a pair of bubbles in the K3. Yeah, that comes from that weight data on so starting from a graph, and our graph is very stupid. It's just an edge with two vertices. We just want to emphasize the geometry part rather than the combinatorics. And just the weights on the vertices tell you other components. It's just specified. Yeah, that's right. By the combinatorial data on the graph on the base. That's right. All right, so let's get gluing. Right, as we all learned from Taub's papers, in the 80s, gluing is a very powerful tool in differential geometry, and so we'll follow along that tradition for this problem as well. So step one is you got to construct a good approximate solution. In this case, well, we have our two bubble regions, and outside of that, we've got an S1 fibration over affine. So we just shoot a straight line. We're on affine. So we start in one bubble, just shoot a straight line out of there, go off and hit the second bubble. And then you just take the pre-image of the circle fibers because you got an S1 bundle there, and that gives you a cylinder. So you just have the cylinder which traverses from one bubble to another. Then you got to cap it off. So a cylinder gets into the bubble, then you got to cap that thing off. Well, if the cylinder runs into one of those monopole points where in the multi-Taub nut the action collapses, that's going to cap it off. So that's going to give us our sphere, which looks like a cylinder, which runs into these two caps on either side. Now that's not going to solve the special Lagrangian equation, but it's going to be an approximate solution. And then so we want to use this perturbation technique to perturb it to a genuine solution. But of course, we got to arrange for this necessary topological condition. If you even want to hope of deforming a special Lagrangian, your integrals better be 0. And so basically that's a question of hyperkähler rotation. So you basically have this lined up thing with a straight line. You just got to align your global hyperkähler structure to be pointing, the complex structure roughly has to be pointing in that direction of that cylinder. And that's more or less what ensures that those integrals are 0. So that's just about arranging. On the ambient K3, you have a whole sphere of complex structures. So since this is a reconstruction problem, like we start from the graph on the base, we set the straight line's given to us, and then we just arrange for the ambient structure to be compatible with that straight line. So that accounts to taking the ambient hyperkähler structure to be pointing in the same direction as that cylinder there. And that arranges those integrals to be 0. So what we want to do is get, from the integrals to being 0 to pointwise being 0, so that we have this special Lagrangian. Okay, so we all know how to deform submanifolds nearby. So if you have a submanifold and you want to perturb it to something nearby, you parameterize the nearby deformations by a normal vector, and then you just use that normal vector to bump it off with the flow. For the special Lagrangian equation, it's customary, instead of taking the normal vector, rather instead you take a tangent vector and you rotate it by 90 degrees with a complex structure J to make it normal. So instead of writing everything in terms of the normal vector, which is normal, you write in terms of a vector which is tangent, and then you lower the index. So actually your deformation parameter is A, which is a 1 form, which is tangent to the submanifold. You use that as your deformation parameter. This is sometimes, this is the standard way to explore moduli of special Lagrangian submanifolds. And let's just write the special Lagrangian equation as F equals A. In PD, we always write F equals A. Let's not write the exact thing. It'll just be F equals A, and A is your deformation parameter. So, F of 0 is not 0, but our approximation solution is nearby. It's close to being a solution. We want to find an A such that F of A is 0. This is general stuff. Many of us have all done this in many different contexts, right? So perturbation fixed point argument. So how do you set up your fixed point argument? Taylor expand your nonlinear function. We want to solve f of a equals 0. Okay, well, we Taylor expand it. F of 0 plus its linearization a plus some quadratic term. And then you rewrite this in a form to apply contraction mapping, right? So one way to do this is introduce this A. So here I'm not giving the specific norms, and this is just like a general blueprint. No matter what gluing you're doing, it probably looks like this, right? So this is just the general formalism that we always do when we're gluing, and you want to show that your this operator n, this operator n, is a contraction mapping to invoke Banach fixed point theorem. And as we all know, what are the keys to getting this strategy to work? You need your f of 0 to be small. Your approximate solution has to be pretty good. You need your L to be invertible. And then also you need, the key thing is often in these problems, the uniform estimate for the inverse of the linearized operator. That's also in our case, the main point. And then you need a quadratic estimate, those Qs, you need a quadratic estimate on those Qs. Those are always the 3 ingredients for any gluing problem. So how does it work in our case? Yeah, I mean, let's just focus on the main point. So yeah, the main challenge is control of the linearized operator. So in our case, the linearized operator is D plus D dagger. And it is invertible. We don't have a kernel because we're on S2. So right, we have these cylinders that are capped off, which are topologically S2. So we don't need to worry about kernel. But what does end up happening is we are not able to get a uniform bound for the inverse. So we do pick up some powers of epsilon as the geometry degenerates. So typically, you see, in many situations, you're able to set up your weighted norms so that these epsilons are taken care of by the weights. So I didn't exactly explain. So in the next slide, I'll explain what's this G epsilon. What's the reference geometry? It looks like collapsing cylinders. I'll show that in a moment. and this beta, C1 alpha beta, there's going to be an appropriate weight function. So these are weighted spaces, weighted holder spaces. And often by using weighted holder spaces, you're able to get estimates which don't degenerate, but here we are not. So I'll get back to that in a moment, but let's just set up the geometry. So all we're trying to do here is put two caps on a cylinder. And our background geometry is roughly dx squared plus epsilon squared. So the S1 circles, they're collapsing as epsilon goes to 0. We want to get uniform estimates with respect to that. So our local models, yeah, they come from, so yeah, so you can see on the caps here, that's this Taub-Nut metric. That's this Taub-Nut local model where you have the H, which is the harmonic function involving this Coulomb potential. That's our local model. We also have global errors on, so this is oversimplified since there's global errors coming from the compact K3 that perturb everything. But roughly speaking, for the first model, our metrics are just kind of like dx squared plus epsilon squared times the fiber. So those are our, that's our reference geometry with respect to which we would like to get a uniform bound on the inverse of d plus d dagger. Right. So here's what happens. We have a problem, which is on a type of approximate kernel forming. So it's because, so at each given epsilon, you cap off their cylinder by 2 caps. That's a sphere, right? Sphere doesn't have kernel, no problem, you can invert it. But as epsilon goes to 0, we're we're collapsing and we're approaching a cylinder. And in one of the blow up limits, when you try to get this estimate uniform in epsilon, in the blow up limit, you see a cylinder. Well, the cylinder has a kernel of d plus d dagger, right? The cylinder has the 2 directions, say dx or d angle, right? So a kernel kind of appears in the limit. And so along the sequence, a kernel is forming, right? So that's why we're unable to get uniform estimates unless, so the first thing we do is we get uniform estimates when we say, okay, let's get perpendicular to that kernel. So you've got, the cylinder has 2 bad directions. It's got those 2 symmetries, right? The translational. If you're thinking about minimal surfaces and you apply J, then you get the normal vectors. You're in a 4 manifold. You've got your 2 cylinder. You've got 2 normal directions to translate your cylinder around. Those 2 directions are the ones causing us trouble. So we want to be orthogonal to that. So that's what we do. So we can get the estimate, no problem. The C is uniform if we're working orthogonal to those 2 bad directions. To access those, you just put in a bump function, right? Because so the cylinder, if you localize to the cylindrical part of the submanifold, then you put those bad directions in with a bump function. Those gives you your 2 bad directions. And we're able to get the uniform estimate in that case. So that's where this estimate comes from. Why are there epsilons? So those are from, we just put in by hand manually those 2 bad directions. So the infinitely many directions, those are good. We have the uniform estimate with a uniform C. We got 2 bad directions coming from the cylinder. So all we did was just, okay, just put them in by hand. So we just had to estimate just working directly with those 2 bad directions. And then we picked up some factors of epsilon. And that's where those epsilons come from. So to be successful in our, oh, I'm sorry. There's this stupid tau. It can be taken to be as small as possible. We just needed us to be a small positive number. We can take to be as small as possible. So it's roughly 1/2 plus a tiny little thing. So back to the gluing strategy, right? So well, that's right. So that's a problem. So when you start bounding the norm of the inverse of L, then you're going to pick up those epsilon to the -1/2, right? So this contraction mapping strategy is only going to work if all your other estimates are good enough to overcome it. So that's what happens. So basically the punchline is our approximate solution is so good that it's able to absorb those epsilons to the -1/2. So that's the reason why the fixed point argument goes through. Nevertheless, even though the linearized operator aren't uniformly bounded, it's because our initial approximate solution is good enough to eat those epsilons to 1/2 and come out ahead to get a contraction mapping. So summary of the gluing construction. As usual, it's the linearized operator. That's the main step. Oh yeah, so that shows you, yeah, so the initial approximate solution is so good, it has powers of epsilon, and it's got this small, I think, roughly 1/100, which is able to eat up this tau, which can be taken to be small enough in order to make the fixed point argument go through. So that's basically summary of the construction. So it's just a gluing construction capping a cylinder with 2 caps, and it's this translational symmetry which comes up to cause some trouble, but in this case, our ambient geometry is robust enough to handle those extra degenerations. So thank you very much.
So thank you, Professor Picard, for the wonderful talk, and we have some minutes for the questions. Is there any questions?
Yeah, thank you for the talk. I want to ask, is it clear if you have this K3 degenerating to T3 mod Z2 and your a general sequence of special Lagrangian, maybe the bounded area or reasonably bounded area will be collapsing to some geodesic nets in T3 mod Z2? Is it generally expected, or
yeah, we want to,
yeah,
the next step is to do that and find all of, exactly, is to find and show basically what you're saying. Yeah, but okay. So for that we'd have to understand. So we want to understand the space of all special Lagrangians for those K3s that are near that limit. And yeah, so we have some ideas, but it's not done yet. So but that they should all be similar things like this. Basically, it should just be a matter of the only possibilities should be things that are connecting these bubbles. So basically what you say is indeed what we expect, but we haven't proved it yet.
Yeah, but is it possible that not a geodesic, but some curve is non-zero, geodesic curvature could also be
no, I don't think so. No, okay. I don't. I would be surprised, but not proved. But I would not expect. I would think they always go to a straight line.
I see.
Yeah.
And is it clear what kind of graph could form as a collapsing limit?
Yeah. So for this case, I think it's going to be stupid. I think it's just going to be straight line connecting two points, or maybe a string of them, a string of straight lines, but we're not going to get any y's. Yeah, that's right. Yeah, I think for this case, it should just be a bunch of straight strings between the points.
I see.
That's right.
Yeah. Thank you.
Any more questions?
Is there any hope for the case of T2 fibrations that something similar can be done to construct via gluing solutions of the form Hormigh and Mills equations?
Oh, well, I was just going to say just the exact same thing. Yeah, I mean, people are working on that. Yeah, so people are working on that problem. That's a very natural problem. And in fact, this whole Sun-Jiang classification, right? Those 1, 2, 3, those are all the possibilities, and each possibility should have its own story in this context of graphs on the base should be lifting to special submanifolds, and in fact, all the special submanifolds up there near that limit should be described in this way by looking at all the possible configurations of graphs on the base. That's the program, and we have all the possibilities by Sun-Jiang, the one-dimensional base, two-dimensional base, three-dimensional base, and all of those are all part of the program. That's right. I'm hoping, in a sense, the one we did is maybe the easiest one in terms of combinatorics. I like the analysis. I'm not a combinatorics guy, so I think in terms of combinatorics, maybe we have the simplest one, although the analysis is still interesting. But in the other ones, there may be some more subtle combinatorics and matching. But we don't see that in our case. It's just a circle collapsing.
Thanks.
Any more questions? May I ask a small question? So what was the, I was curious, what was the weight you mentioned on your Holder space, the beta weight? What was that?
That's right. Oh, well, okay, the weight itself is just it turns out to be a small negative number, as often is for gluing constructions, just a small negative number. But the actual weight function.
Yeah, what was the weight?
Yeah, so it's this here. So it's like you have a cylinder, you've got x direction, and then you have a circle direction. And
Yeah.
you put the weight only on the x direction. So the circle, the S1 direction, doesn't have a weight on it. So it's this sort of ALF type weight rather than a cone. So that's what's written there. So it's just roughly like a norm of x, where x is the direction on the base of the cylinder. And that's the weight. And then so in the weighted norms, you just put those factors of x into some power beta, where the beta has to be very small. And that allows you to invert the linearized operator when you do
I
blow
guess
up.
that's kind of some kind of standard. That's
Totally,
scattering. Yeah.
that's totally standard. Yeah, exactly. That's right.
All right. Any more questions? And thank Professor Picard again. And we'll come back after a 15-minute break.
1、2、3。
All right, it's my great pleasure to introduce Professor Lanxuan Huang to give us the final talk of this afternoon section here, and titled on the boundary value problems for Einstein manifold. Welcome.
So thank you very much. And it's really my great honor to be here to celebrate the milestones of geometry analysis, but in particular for Leon's birthday. So Leon is my teacher, and he's really a great teacher. And in fact, he won a major teaching award while I was at Stanford, and we all went to his celebration ceremony. And one thing we really like is his energy when he teach, and he jumps, especially when he talk about important topics. So it shows, so he was also in my thesis defense committee. And this was my last slide for my defense. And you can see that's the energy level we admired. That was many years already, right? But I have to say, Leon is still the same as I remember him, and even more. So I think I found typos on the conference title. Are you sure it's not the 18th birthday of Leon Simon? Right, so this should be a typo. All right, so today we'll talk about Einstein manifolds, right? So the Einstein manifold starts in general relativity, and the Einstein's field equation says the left-hand side is a curvature, and that describes a gravitation, and it equals the right-hand side T is the matter field. So good summarize from John Wheeler, physicist John Wheeler. It says matter tells space-time how to curve, and the curvature tells matter how to move. So that's the interconnection between these two quantities. And what's really meaningful about general relativity is you also make Riemannian manifold alive, right? So if you take a time slice of the space-time, so there will be a induced matrix and induced second fundamental form. So if you look at so-called time slice, then it will have an induced Riemannian matrix. And then once you have this induced quantity, and then you can start to looking at what Einstein equation induced on the time slice. So the matter field, T in the NN direction, N is the unit normal of the hypersurface. And by the Einstein equation, you can combine with the Kodály equation, and you get this one. So all the quantity are the quantity in terms of initial data, this G and K. And then the cross term from the matter field, use Kodály equation, you get this. So that's a dynamical term. And the so-called energy condition. So there are various energy conditions in general relativity, which usually means some positivity about the matter field. So particular like a dominant energy condition will imply the matter field is positive in the sense when you have observer, the energy flux measured by the observer is non-negative, then that will becomes this condition. This TNN components is bounded by the norm of this cross term. And so in particular, in the case when K is not there, right, the time symmetric case, it becomes the non-negative scale curvature. People also look into the umbilic case. That's when G equals K, and then you do some computation, you find out let's give you like a scale curvature greater equal to some negative lower bound. So the Riemannian manifold really, you can think about it sitting in the bigger space. So that's for the general energy condition where the T is there, but many important cases are already there when T is actually zero, so-called vacuum case. So for example, the first non-trivial vacuum space-time solution is the Schwarzschild space-time. And then probably the next example is the Kerr space-time. So they are both the vacuum space-time solution, and they are exact. So in a sense, they can write down the matrix components exactly. And Schwarzschild space-time is the one major so-called static black hole. So this is really just a not so serious picture. Think about you have a black hole which suck everything inside, but it's not moving, right? Being static, just say everything stay the same as time evolve. And the current solution is also a solution to the black hole, but it's rotating. So it's rotating in time. So those are very important solutions, and they are singular actually. So in Lorentzian manifold, so we sometimes actually you have incomplete matrix, singular matrix is actually good. But either in the Riemannian or the Lorentzian case or space-time, we can define the Einstein manifolds, which are just the same way the Ricci curvature is constant. In the sense, it's constant multiple of the matrix. And people will have different ways to argue there are the canonical geometries on manifold, and also they include many important non-trivial examples. So let's have some basic sense about this condition. So let's look at the case of surfaces, two-dimensional, right? For surfaces, the Ricci is actually completely described by the Gauss curvature. And then we have the uniformization theorem, which says every simply connected Riemann surfaces is conformally equivalent to exactly either the sphere, the complex plane, or the hyperbolic space. So consequence, every manifold, if you pass to the universal cover, and then that has a canonical matrix, the constant scalar, constant Gauss curvature matrix, and that means every manifold admits the Einstein matrix. So that's not very interesting in the two-dimensional case. And in the three-dimensional case, in fact, the Ricci curvature also complete determines the sectional curvature. Then we have the space form theorem. Say the complete Riemannian manifolds with constant sectional curvatures has to be the model space, either quotient of the sphere or hyperbolic space or Rn. So a consequence is if we have a closed three manifolds, which admits the Einstein matrix, if it's space form. So all the Einstein matrix on three-dimensional manifolds are trivial in this sense, they have constant sectional curvature. But also it tells you there's some topological abstraction. So many three manifolds, they are not space forms, right? Such as this one. So those manifolds do not admit Einstein matrix. So really the interesting examples start with 4-dimension. So the 4-dimensional case, the Riemann curvature tensors decompose into the trace part that's Ricci and the traceless part that's the Weil curvature. And there are many non-trivial examples exist, starting with the Calabi-Yau manifolds, the first family of non-trivial examples. And then after that, there are a lot of other examples, for example, like a complete non-compact case, like a so-called gravitational instantons. But still, construct Einstein matrix on a closed manifold is extremely hard still. So, but why do we expect we can find more Einstein matrix, right? So there's a PDE perspective. So Einstein matrix or Einstein equations, they're actually geometric PDE. So if you write down in the harmonic coordinates, the Ricci can be written down as a second derivative of the matrix components, where the box G is the trace using the matrix. And then you have the lower order term, the quasi-linear term, only involving G and partial G, so no second derivative. And really depends on the signature of the matrix. So if it's Lorentzian matrix, then the box is a wave operator. And if it's Riemannian, then it becomes a Laplace operator. So solving Einstein equation in some ways like solving quasi-linear, either wave or Laplace operator. But of course, the biggest problem is there's usually no global harmonic coordinates. But still from those PDE perspective, there is some significant results we know about Einstein matrix. So Einstein matrix share many similar analytic phenomenon as the solutions to either wave or elliptic equation. For example, in the fundamental theorem, Cauchy problem in general relativity is solved by this observation. So give vacuum initial data set, so given a G and K, like on a Riemannian manifold, and then the equation of Ricci flat becomes a quasi-linear wave equation in harmonic coordinates. And then by choosing the suitable initial condition, And then Shoker-Bruja show you can actually use it to evolve and develop a vacuum space-time. And also, we have a unique continuation, the strong rigidity for Einstein matrix. Because we know the harmonic function is analytic, right? So similarly, if you are written the matrix components of the Einstein matrix in harmonic coordinates, it satisfies the PDE, so it's analytic. The matrix components are analytic. So if two Einstein matrices agree on the open set, they must agree everywhere. It's agree on the fixed coordinates, right? Right. So, right. So I think if you agree on one coordinates, and then you can transform together to the harmonic coordinates. So yeah, so it's actually in geometric uniqueness. And also it has been observed by Anderson, this property, the PDE property can be used to derive pretty strong compactness results. So the sequences of Einstein matrix actually has C1 alpha convergence subsequence. So the key thing is really to have the harmonic coordinates in a uniform size. And for example, Ricci flow, right? Just writing down the PDE, of course, is highly non-trivial work in Hamilton until de Turck found out these harmonic coordinates analogous in the parabolic case. So you can get short-time existence for Ricci flow. So I'm not sure if Leon worked on Einstein matrix directly, but his PDE techniques has been really highly influential. So in this really seminal work, where he showed the uniqueness of the tangent cone for minimal surfaces, he introduced the Hoyasiewicz-Simon inequality, right? It has been extremely powerful. For example, Cody Minicozzi using this concept to show the uniqueness of the tangent cone for Einstein manifolds. Okay. And today we want to talk about Einstein matrix with boundary. So the guiding questions is really how can a geometry of an Einstein manifolds be determined by its boundary geometry? So these kind of questions appears in many settings. I only list two. So so one type of question is you actually think about the boundaries at infinity, and you are looking for the hyperbolic Einstein fillings, right, with conformal boundary. And so for example, that's part of the Feynman Graham program and highly energized by in theoretical physics the ADS CFT theory. So you want to know once you have a conformal structure at infinity, and then can you find a unique filling or not, and which is Einstein. And in general relativity, also highly related to the quasi-local mass. So quasi-local mass is once you have a compact set, you want to know how much gravitational mass is contained inside, right? And there are a lot of various boundary conditions. And then, for example, if the boundary condition tells you the mass is 0, can you determine inside the compact set is actually rigid? So we will first discuss the Riemannian case. So if we have time, we'll talk about a little bit Lorentzian case. So we'll talk about the Riemannian Einstein matrix on manifold with compact boundary. But now the boundary is at finite distance, is no longer at infinity. So this kind of questions has also been studied very recently in the physics community. They usually sometimes call the finite ADS CFT theory. Instead of boundary at infinity, is actually finite distance. Once you know the boundary data, can you find the Einstein matrix inside? So of course, what would be the boundary condition for Einstein matrix, right? A very natural one will be the induced matrix, because the induced matrix is analogous of the Dirichlet's boundary data, right? The restriction of the interior matrix. Then probably next natural one will be the Neumann boundary condition. There'll be the induced second fundamental form, because the second fundamental form is roughly like a normal derivative of the matrix. So it's like a Neumann boundary condition. So those two are the most fundamental boundary conditions we study for harmonic equations. But unfortunately, those two boundary conditions are not elliptic. So since if we want to work with the Riemannian case, we want to work with the elliptic PDE, right? So if the boundary is not elliptic, we usually really don't know how to even find existence or regularity type of thing. So Anderson proposed another type of boundary condition, the mixed boundary condition, and we call it Anderson boundary data, which is instead of you prescribe induced matrix, which is too much, right? But you are allowed to remove this conformal part. So you only prescribe the conformal class. Sorry, the conformal class. And then, but now you have one more equation to prescribe, and then you use the mean curvature. So this is the pointwise conformal class of the induced matrix on the boundary, and H is the mean curvature. And Anderson showed that this is elliptic. So elliptic really means you choose a suitable coordinates or gauge, and then under that gauge, it can be written down as elliptic system of equation. And there's also a promising phenomenon is there's a short-time existence of rich flow with the Anderson boundary data by John Niotis in, I think it's 2016, quite recent. I think the original motivation is to use this flow to find the Einstein matrix inside, right? With given boundary data, Anderson boundary data, can you find Einstein matrix inside? But he can only show short-time existence. Right? And so also we want to know how many solutions we get. And the Einstein equation and the boundary geometric boundary condition is diffeomorphic invariant, right? So that means you can have one solution, right? Write down this matrix as an n by n matrix. And then, but you do a diffeomorphism change, you completely write a new matrix of this 2 by 2 of these two tensor. But it turns out they look different component-wise, but they are actually the same. They are just different by diffeomorphism. So that's the geometric invariance of this equation. So to really count how many different solutions you get, we have to quotient out the diffeomorphism group. So the setting is, so let lambda to be the Einstein constant, the one we define the space, and omega is a compact connected manifolds with smooth boundary. And this is a space of Einstein matrix. But then there is geometric invariant, so we quotient out all the diffeomorphism group. But the tricky thing we do here, or Anderson did, is he restrict the diffeomorphism to be identity on the boundary. Because we want to fix the boundary condition, right? So he fixed the diffeomorphism to be identity on the boundary. And which somehow is surprisingly good, because if you look at the moduli space, usually we worry about when moduli space will become like an orbifold or like singular when you have non-trivial isometry. But then we know if you have a isometry which is in the codimension 1, so the identity set has to at least codimension 2, right? But the boundary is identity. That means the only isometry must be the trivial map. So he shows under this condition, suppose the relative fundamental group is trivial, and then this moduli space is actually smooth. And in fact, it's infinite dimensional smooth Banach manifold. So if it's not empty, if it's not empty, actually you will have one solution implies you have infinitely many solutions. And further, he showed is really good for apply elliptic theory is the boundary map. So given Einstein matrix and you send to the Anderson boundary data, is a smooth map and the Fredholm index 0. Okay, so this he also mentioned he's not sure this condition is needed, but he need in the argument, but it's not clear where this condition can be removed. And this condition says the sigma, the boundary has an inclusion map inside omega, right? Because it's subset. And then the induced map between the fundamental groups has to be surjective. So that means all the topology is contained on the boundary. And physicists told me it's quite reasonable condition because they have like quantum field theory sitting on the boundary. And So first, this also implies the boundary has to be connected. And they told me if you have two connected components, and then you have two probably incompatible quantum field theory, and which somehow will connect inside, it doesn't make sense. And also somehow the quantum field theory have all the information already contained in the boundary. So, but in any case, that's the condition he needs to get this nice Fredholm property and smooth banana manifold. Okay. And he also made a conjecture, say, assume the relative fundamental group is trivial, and the boundary map is actually regular. And it's regular at generic matrix in the moduli space. So regular means the linearization is surjective and the kernel split. So if what this statement really says, so for generic G, such as the map is regular, and this linearization is in particular surjective, that means the map, the nonlinear map is local surjective. So local surjective means once you know you have this boundary data from one Einstein matrix, and you can perturb it, right? It's locally surjective. So you can perturb it, and then you will find a solution inside. So you'll find for any perturbed boundary data is realized by an Einstein matrix. But instead of thinking about that's the existence result for Einstein matrix, remember 3 dimension is very special, right? It's actually the constant sectional curvature. So this probably is better to view this statement as the admissibility of conformal immersions into space forms with prescribed mean curvature. So in other words, if you have given a conformal structure on sigma, which is a 2-dimensional surface, and then you give a number or function, mean curvature on it, and you ask whether you can find the immersion into your space form, say R3, which you realize this data. So it's a bit related to so the talk we heard about before about Bonnet pairs, right? So you have this induced matrix and then mean curvature. Does that uniquely determine the surface or not? So this question is like a relaxed. So instead of induced matrix, if you have a conformal structure and mean curvature, does that give you immersion? Okay. So this conjecture is actually a baby version of a more general conjecture of Anderson, which really asks or more general questions like, for what boundary data here, you can guarantee there is an immersion into the space form. And he developed the degree theory. So he wanted to show this map is degree, say 1. If it's degree 1, means you will always have a solution, right? But it turns out it's very difficult. He could not show it. He has a modified version, but it doesn't apply to this boundary map directly. So it's still not clear under what condition of this pair you can find immersion, realize these two. And about genericity, in fact, the genericity cannot be removed. So there are example actually by round balls, the simplest example we have. So in roughly speaking, the mean curvature is abstract. So if it's regular at round ball, that means for any nearby mean curvature, it can be realized as a conformal immersion, right? But in fact, there's coming from the conformal Killing vector field of the round sphere, which tells you the mean curvature cannot be arbitrarily prescribed. So this also cannot remove the generic in the statement. So what we wanted to show is we show this conjecture of the baby version. That conjecture is true. And so everything I talk about today is a joint work with Zhongshan and An Zhongshan. So she's a really bright young mathematician in UTSC. So what we show is the previous conjecture holds. Let me restate it. So for 3-dimensional manifold with omega, with this relative fundamental group trivial, and then the boundary map is a local diffeomorphism on generic matrix. So the previous say is regular, but together with the Fredholm property, we actually know is a local diffeomorphism. So in other words, the nearby Einstein matrix are parameterized by the Anderson boundary data. So you can somehow, it's infinitely many, right? But you can order them by using the Anderson boundary data. You can label them by the Anderson boundary data, at least locally. So of course, we are also interested in higher dimensional case, right? Because that's where the Einstein equation really thrive. So we are looking at a higher dimensional case. So here we are showing the relative fundamental group is trivial as before, but it turns out we need a strict stability condition on the boundary. And assuming this condition, the Einstein constant also make a difference. In the case of Ricci flat, zero Einstein matrix, it's a bit easier because so in the Ricci flat case, if we're looking at the space of Ricci flat matrix, but now we restrict them with the strict stable boundary condition. So this is open condition. So this will be open subset in our previous general space. And then we're still looking at the moduli space, quotient out the diffeomorphism. And we have the same statement as before, but with the smaller like a space, which those has strict stable boundary condition. So the boundary map is a local diffeomorphism at generic matrix. And for negative one, things get a bit evolved. So here we're looking at the negative Einstein matrix, which is not the one fixed Einstein constant. We are not able to pinpoint which Einstein constant we can construct the matrix. But then we're just looking all of them together. So it's negative Einstein with strictly stable boundary. Also, we need to assume it's mean convex. And then under the space, we show the boundary map. So from the Einstein matrix to the Anderson boundary data is regular, but it's not local diffeomorphism anymore. Instead, it has a one-dimensional fiber. So given the boundary data, we can actually find one-dimensional family of Einstein matrix. And the thing is, we cannot control the Einstein constant. It turns out it's highly related to the volume, which is also global quantity, and we cannot separate them. Yeah, very good question, because that's in my next slide. Not yet, but I will get there. So the main principle of those theorems is for generic good, in the sense if you have a strict stable boundary, and they are locally parameterized by Einstein boundary data. So what's strictly stable boundary? So, so in a nutshell, it's a boundary operator defined. It's an elliptic operator defined on the boundary, and then either the first eigenvalue is positive or the second eigenvalue is positive. Okay. And then, but in the special case, it actually has some geometric meaning, which we are still exploring. In the case, if mean curvature is constant, our strict stability condition becomes requiring the boundary matrix is a strictly stable critical point of this functional. So this is the volume normalization Einstein-Hilbert functional, and among the non-homothetic conformal transformations. In other words, you can write this as the Yamabe quotient, and then we need that matrix to be a strictly stable critical point of this functional. So for example, sphere. So we talk about round ball, and the boundary round sphere does not satisfy this condition because it has a non-trivial kernel. So it's only stable, but it's not strictly stable. But there are examples of stable boundary. So the Euclidean-Schwarzschild is the one, the Schwarzschild-Lorentzian matrix, by doing this amazing weak rotation, right? Make it Riemannian. And then you do some identification to identify the period to make it complete Ricci flat matrix. So this is the picture from physics paper. And I have to agree, it's hard to visualize the construction. But then the upshot is those are smooth, complete, Ricci flat Riemannian matrix. Okay, and then now we're looking at this sublevel set by R, by the radius. And each of them is of this topology. So that's a bounded region, that's a compact manifold with boundary. And then we compute their the street stability condition, and all of them have strictly stable boundary for all the radius. And we also do the computation in higher dimensions. And it turns out in higher dimensions, there are only certain radius, like either radius very large and very close to the critical R0. There's some interval in between, which does not satisfy this condition. But at least in 4 dimensions, I think it's very interesting. Like every of these sets has strictly stable boundary condition. Okay, so how about just a few words about our proof? So the boundary value problem for Einstein matrix really resemble the familiar elliptic PDE. So for example, our approach really, you should think about is analogous of these results is if you have a domain and you want to solve this like a Schrodinger type equation. And on the manifold with boundary and with direct boundary value, say, and in general, you don't know if you can solve the equation or not, right, with the prescribed boundary value, because it may have kernel. But by Fredholm alternative, if you know the kernel is trivial, then you can solve the boundary value problem. So you want to, so on the fixed domain, this operator may have non-trivial kernel. But then if you do the inward domain deformation, and then the kernel will disappear. So as the domain varies through the inward deformation, the boundary value problem becomes solvable except for isolated values of t. T is like how you label the inward deformation. And our Einstein boundary value is similar. But then the main challenge is for the PDE to be elliptic, we need the harmonic coordinates, right? But actually those coordinates, they do not work well with these mixed boundary conditions. So it's a bit similar, like usually the classical proof of this fact involve the Rayleigh quotient, right? But there's no Rayleigh quotient for this operator, just because when you do integration by part, there's undesirable boundary term appear, which has nothing to do with the geometric boundary condition. I think I need someone help me to get rid of the top thing. Right, thank you so much. Thank you. And just roughly what the proof goes. So really we use implicit function theorem, right? So we want to show the operator is diffeomorphism. So we want to show the linearization has trivial kernel. So the linearized problem looks like this. And this beta H term is coming from so-called gauge, harmonic gauge or Bianchi gauge. And then we have the geometric boundary condition. This is conformal. This is the mean curvature, but you linearize it. And then we want to show if you have H, which is a symmetric two tensor, satisfy this system of PDE and equals 0. And H is actually 0. It's really 0, right? Because we fixed the gauge already. But our idea is somehow we can use in this inward deformation to create, so we do the second variation of the Hilbert-Einstein functional, and then we create a green type identity. So somehow this inward deformation gives us a good test function to work on. So that's probably the main part of the proof. And using that, we can upgrade these two vanishing Anderson boundary condition to a stronger Cauchy type boundary condition. So it's very similar, like if you have a Dirichlet's boundary value, but you want to show it actually satisfy additional Neumann boundary condition, then it will be overdetermined. And once you have an overdetermined boundary condition, it has to be trivial. So we'll upgrade to a Cauchy type boundary condition. And then using our green type identity, we show that we can do a good test function, and we find out this non-negative quantity has equal to the right-hand side. And the right-hand side, the good thing is when n equal to 3, this cancel, this is 0. So when n equal to 3, it doesn't matter what this term is. It's always 0, right? The coefficient is 0. So then we upgrade from only the linearized mean curvature 0 to this, we call the conformal Cauchy boundary condition is 0. And once we get that, we show unique continuation in this setting. In the higher dimensional case, this is no longer 0, but we observe this can be written in terms of elliptic operator, which is really the linearization of the scalar curvature on the boundary among the conformal deformation. So then our stability condition comes in such that this has opposite sign, right? Then let's show both term will be 0. So that's the one slide proof. I think I will talk about it a little bit about the Riemann Lorentzian setting. So our reason we're interested in the Einstein matrix is because really coming from general relativity, there's so-called the static vacuum space-time. So Lorentzian, I have to say, construct Ricci flat Lorentzian manifolds are extremely hard, right? So we have this beautiful Choquet-Bruhat theorem. But then once you are looking for a global solution in time, right? And it's really, really difficult problem because you have to know the evolution equation of the wave equation. It's extremely hard. But there's the way to cheat is you're actually looking at the static space-time, nothing move, right? If nothing move, then you actually just need to know the initial data set and that determines everything. So that's what static space-times are. So the static vacuum matrix are the time-independent solution of Ricci flat. So you really just, it's space-time, but you just look at the slice. And a slice, that's called the static vacuum matrix. It's a Riemannian manifold. But then you have an additional function which coming from the time translation Killing vector field. So together, this matrix and the U will satisfy this system of equations. So U has to be harmonic on the Riemannian manifold, and the Ricci has to be somehow like a Hessian of the U. And once, if you know U is positive, and you can use it to construct a Ricci flat spacetime, and that exists for all time. There's a global in-time solution. So for a static vacuum matrix, you can see that's very similar to the Einstein equation, right? It's essentially Einstein equation plus some information from the scalar function. And you can also ask whether you can solve the one with boundary condition. And from various studies like positive mass theorem and a lot of gluing construction and scalar curvature deformation, it turns out this Barnick boundary data is the right one to consider. So that's the, now it's the induced matrix together with the mean curvature. Okay. So it's very interesting, like you have no boundary condition on you. Actually, you cannot impose boundary condition on you. And compared to Einstein equation, because now we have one more unknown, right? So we can have one more freedom equation. That's why we can get rid of this conformal part. We can actually consider induced matrix completely. And the questions coming from the quasi-local mass is, does the boundary geometry, like given this boundary data, does that determine a canonical static vacuum asymptotic flat extensions? One can also ask about the fill-in, but fill-in, in fact, is harder, much harder, a little bit harder question. Extension, we have more results. So they're closely related to the quasi-local mass or equality case of positive mass theorem and scalar curvature gluing. And we use essentially very similar idea. Of course, the techniques, the equation-wise are pretty different. It's also joint work with Zhongshan. So what we show is near a stable asymptotic flat static vacuum background. For example, what are stable? Euclidean space is stable. Schwarzschild is stable. And then the nearby Barnick boundary data are realized by locally unique nearby static vacuum extensions. And more precisely, we show its extension, right? So we're looking at the background is the exterior region of some background static matrix. So we show for the exterior of star-shaped regions in Euclidean space, we can find the nearby boundary data. So it's a perturbative result. And that generalized the previous result on Miao, Anderson, Curry, Anderson, which is on the round ball. We also show the generic exterior regions. We can perturb the Einstein matrix. We can perturb the boundary data to get to get static vacuum extension. And then we show that for generic exterior regions in Schwarzschild. So you can see in this case, we do that case by case. In each case, we have to show this linearized operator has a trivial kernel by choosing specific test function to get this upgraded boundary data. And then we show for the remove the genericity, but for the round balls in Schwarzschild. So that's a joint work with Spiro Alexakis and Ahmed Alisi. So in fact, originally they are trying to find counterexamples on round spheres, but it turns out it's also true for those round spheres. And Alisi has a separate proof for the Schwarzschild, a different proof, and he also recently generalized to so-called the stationary vacuum spacetime. In the recent work in preparation is we did all this result case by case, but there's actually a unified approach removing this genericity. So we can show all the exterior regions in those good static vacuum background, like a Euclidean, like a Schwarzschild, they are actually all are perturbative in the sense you can perturb the boundary data to find static vacuum extensions. And that's the observation. See, this linearized problem, whether the kernel is trivial, can be think about as eigenvalue problem, and then we can show the eigenvalue is positive, really using the positive mass theorem, AD and mass stability. But it's in preparation, so I will not talk about too much detail on that. And why people are interested in static extension? Because Barnick, from his Barnick quasi-local mass, has a conjecture question is what kind of suitable boundary data will be good, right? So given suitable boundary data, there exists a unique asymptotically flat static extension realized in those boundary data. So our perturbative results suggest this problem is locally well posed near stable backgrounds, static vacuum matrix. Of course, this question should be think about like whether it's globally well posed, and we are far from that question. Okay, so, all right. So here we learned Leon has several phrases, right? I will give you some more. So we learned a lot of math from Leon, but we also learned the taste of math from Leon. So he said, PDEs are the language of geometry. I think many of you here probably agree with me. He also told us hand waving is not a proof. So every time in our GMT seminar, someone hand waving it, he will say hand waving is not a proof. And if you cannot make it rigorous, then you don't yet understand it. And next, one of my favorites is theorems are not there to be admired. They are there to be used, right? So I think really inspires us to use theorems, but also prove useful theorems. I have a long list of really good things we learned from Leon, but Leon also told us flattery doesn't get you very far. So I think I will just stop there. Happy birthday, Leon. I'm pretty sure you did. Wow. Right.
So thank Professor Huang very much for the wonderful talk and interesting stories. So any questions about the talk?
Thank you for your nice talk. My question is stable asymptotic flat static manifold a minimizer of mass in certain sense?
Exactly, right. So we heard about a lot of stability in my talk and also in many talks, right? So the stability in the, let me go back to my slide. And the stability here is really in the ADM mass stability. So in a sense, like a positive mass theorem tells you the Euclidean matrix is a stable critical point of the mass functional. And then the Penrose inequality tells you the Schwarzschild is a stable critical point of the of the mass functional among suitable class, right? Among those asymptotic flat manifold with minimal surface boundary. So that's lot stability. But what we need is a strict stability. So we actually have to show their second variation is strictly positive of the mass, ADM mass functional.
But is there any relation with ideal value of issue knowledge refraction?
Exactly, right. So that's in fact, so in the linear, when you compute the mass, you actually compute the so-called rigid Heiterbone functional. It's the mass minus the total integral of a scalar curvature. And the linearization is the Linear-Schroelich operator. So it's in some sense, that's a spectral positivity in the case of this asymptotic flat manifold. And mass is there to cancel out the boundary term when you do the variation, right? So that's the same thing as you, but the question is what class of deformation you allowed in your spectral stability, right? So the one here, it really depends. We need, for Euclidean space, you just need compactly supported deformation. And among those, the Linear-Schroelich operator has strictly positive eigenvalue. In the Schwarzschild case, you probably have to really think about what kind of H you allowed at deformation on the boundary, right? Because if you restrict, it's not enough to restrict over only compactly supported. You need to allow the boundary to have some deformation.
And does anybody else has more questions?
Thank you for a great talk. When you proved the property of boundary map, you said it's a local diffeomorphism at general metrics. Did you have to use any kind of gauge fixing?
Yes, right. So the gauge is actually the big problem here. So for ellipticity, we use this one, right? And then once we fix gauge, we need to show the kernel here is really zero symmetry times H is identically zero. But then in other parts, whenever we need the boundary integration by parts, you cannot use this gauge. So we actually have to change between harmonic gauge and geodesic gauge. And that's really the main difficulty of this type of boundary value problem.
So maybe this is somehow remotely related to your research, but do we expect more structures on the moduli space M lambda mod diffeomorphism group? Because do we expect anything kind of like a slice theorem on these spaces?
Right. I think we do have a slice theorem in the sense like if you choose the gauge and then you have a unique representative locally, right? But I'm myself is also learning in this field. So can you probably tell me what kind of structures are you looking for? So I learned this for the closed manifold. There's a question still open is whether in that case the moduli space is not smooth in contrast to our case, right? Our case, the moduli space is smooth. And for the moduli space of Einstein matrix on closed manifold without boundary, and it can have singularity, but the open question is show it's actually only orbifold singularities, and which is, I don't know, but I'm also curious, like once we know it's smooth Banach manifold, what additional structures would be interesting to consider?
Koizo in the 80s discussed in the company closed the case, right? Are there any extensions for his work to the boundary?
That's a very good direction. So I know he showed for the closed manifold, the moduli space has at most finite dimensional, right? So that's why it's so hard to find Einstein matrix on closed manifold. I don't know what additional structures he proved, but it would definitely nice to see. So in our case, it's infinite dimensional. So the analogy of finite dimensional is no longer true, but probably, I have to go over the paper and find some interesting structure to prove. Do you know any?
Okay. Yeah.
This is like a really relatively new direction. Einstein, the Anderson boundary condition was, I think, proposed in 2008, but I think it brings more attention just recently when people, especially from physics, they are looking at the Euclidean quantum gravity, but in the finite region, and they're looking for the good elliptic boundary condition. So it turns out they also found this one.
All right, so thank the speaker again and thank everybody here for the participant. I hope to see you soon.
All right, thank you.
Thank you.